I want to start with a calculation because this entire film is a consequence of it. And if the calculation lands, then everything else is just detail. Take a language model with 70 billion parameters. That is a mid-size model by current standards. Not a frontier system, not a toy. Each of those parameters is a number, and in the most common serving format, each number occupies 2 bytes. 70 billion parameters, 2 bytes each, is 140 gigabytes of weights. Now ask it for a single token, one word roughly. To produce that one token, the model performs a forward pass, and a forward pass touches every weight exactly once. Not most of them, not the relevant ones, all of them. There is no mechanism in a dense transformer by which a weight sits out a forward pass. So producing one token requires reading 140 gigabytes out of memory, and into the arithmetic units. The fastest widely deployed accelerator for this work is NVIDIA's H100. In its SXM form, it carries 80 gigabytes of high bandwidth memory, and that memory delivers 3.35 terabytes per second. That is an extraordinary number. It is roughly the entire printed contents of a large university library, every second. So, 140 gigabytes at 3.35 terabytes per second. Divide, and you get 42 milliseconds. 42 milliseconds per token as a floor, not as a measurement of some inefficient implementation, as a floor, a hard one. That is the time required to move the numbers, and you cannot produce the token without moving them. 42 milliseconds per token is about 24 tokens per second. That is the theoretical ceiling for that model on that chip, at batch size 1, before you have accounted for a single other cost. Now here's the part that should bother you. That same H100 is rated at 1,979 teraflops on half-precision tensor operations. 2 quadrillion arithmetic operations per second. And in the calculation we just did, arithmetic never appeared. Not once. The answer did not depend on how fast the chip can multiply, because the chip was never waiting on multiplication. It was waiting on delivery. You could double the arithmetic throughput of that chip, quadruple it, put 100 times more arithmetic on the die, and the answer would still be 42 milliseconds. You would simply have built a larger machine to do the same amount of waiting. I want to be precise about how much waiting. A forward pass at batch size 1 reads each 2-byte weight and performs exactly 2 arithmetic operations with it, 1 multiply and 1 add. 2 operations per 2 bytes, 1 operation per byte. Hold on to that number because it is going to come back in every act of this film. The H100's ratio of arithmetic to bandwidth is 1,979 teraflops divided by 3.35 terabytes per second, which is 591 operations per byte. The workload supplies the machine wants 591, which means that during the generation of a token, the most expensive commodity processor ever manufactured is using approximately 0.17% of its arithmetic capability. The other 99.83% is present, powered, thermally managed, and has nothing whatsoever to do. Let me put that in terms of the object rather than the percentage. This chip costs roughly as much as a car. A reasonable car, it draws 700 watts, which is a hairdryer running continuously. And it is cooled by infrastructure that costs more than the chip. And during the task it was purchased to perform, it is essentially standing in a doorway holding a single number, waiting for somebody to bring it another one. I'm going to come back to this image repeatedly over the next 3 hours. So let us establish it properly now. The GPU is not slow. The GPU has finished. The GPU finished some time ago and is waiting patiently at enormous expense, like a very costly dog that has brought you the ball and does not understand why you're not throwing it. This is not a bug. Nobody made a mistake. It is a consequence of a physical fact that governs the whole of this subject, and the film you're watching is an attempt to trace that fact from the transistor all the way to the token. The fact is this: arithmetic is nearly free. Moving the numbers is not. Everything else, the design of a GPU, the existence of CUDA, the cache hierarchy, tensor cores, why your model needs VRAM and not an SSD, why inference is slower than you expect, and training is expensive in a completely different way, why the industry is quantizing everything in sight. All of it is an answer to one question, asked over and over in different costumes. How do you avoid moving a number twice? Let me put a price on the claim I just made, because arithmetic is nearly free is the sort of thing that sounds like rhetoric. The relevant currency is not time. It is energy, joules per operation. Energy is the honest unit, because in a data center, energy is what you actually buy, and because energy per operation is what ultimately sets how much computing a given power budget can deliver. A picojoule is a trillionth of a joule. It is an absurd unit for anything human. A single AA battery holds about 10,000 joules. 10 to the 16th picojoules. You're never going to feel a picojoule. At a modern process node, a single floating point addition costs on the order of 1 picojoule, a multiply costs a few. These numbers move with process technology and precision, but the order of magnitude is stable. Arithmetic on a chip costs picojoules, singular, low. Fetching the operand for that addition from off-chip memory costs several hundred picojoules. Read that again because the ratio is the entire subject. The operation costs 1. Getting the number to the operation costs hundreds. The computation is a rounding error on the cost of delivery. And the ratio is not a fixed insult, it is a gradient, and the gradient follows distance. Pulling a value from a register, which is a handful of transistors sitting directly beside the arithmetic unit, costs a small fraction of a picojoule from on-chip cache. More from further out on the chip, more again. From memory on the other side of the package, hundreds. From storage, we are no longer in the same conversation at all. Physics is doing something very simple here and being very stubborn about it. Moving a bit means charging a wire. A longer wire has more capacitance. More capacitance means more charge. More charge means more energy and more time. The cost of a number is a function of how far it traveled to reach you, and that function is not kind. This gives us the sentence that organizes everything. Distance, cost, energy, and energy is the real budget. Now consider what that means for the machine we described in the last beat. The arithmetic units of an H100 are ready to perform 2 quadrillion operations per second. Every operand they consume has to arrive from somewhere. If it arrives from a register, wonderful. If it has to come from HBM memory that is on the same package inches away, about as close as off-chip memory can physically be, it costs hundreds of times more energy than the operation it feeds. So a chip designer's job is not really to build fast arithmetic. Fast arithmetic is the easy part. You can always buy more of it by spending area. The job is to arrange things so that each number, once fetched, is used as many times as possible before it is thrown away. Every reuse amortizes that fetch. Every failure to reuse pays it again. That is what a cache is for. That is what a register file is for. That is what tiling is for. And blocking, and the entire discipline of what people rather grandly call data locality. It is all one idea, wearing different hats. You paid to move that number, so use it more than once. And it explains the shape of the problem we opened with. At batch size 1, you read a weight, you use it twice, and you discard it. You paid several hundred picojoules to deliver a number, and you extracted about 2 picojoules of work from it before letting it go. You're running a delivery service that ships 1 item per truck. I want to be clear about the scale of that inefficiency, because 1 item per truck is not hyperbole, it is roughly the literal ratio. You dispatched a vehicle, drove it across the country, and delivered a paperclip. Then you did it again. You did it 70 billion times, and that produced 1 word. And then to produce the second word, you did all of it again, the same 70 billion paperclips, along the same route, in the same trucks. Because nothing you fetched was kept. Hold that image. In Act 4, we will put more items in the truck, and the entire economics of inference will change. None of this is new, and the people who saw it coming were remarkably clear about it. In 1995, William Wolfe and Sally McKee published a short paper with a title that has outlived almost everything else from that year's computer architecture literature. Hitting the memory wall, implications of the obvious. Their argument was almost aggressively simple. Processor speed was improving at one rate. Memory speed was improving at a slower rate. 2 exponentials with different exponents do not stay close. They diverge, and they diverge without limit. Extend the lines far enough and you reach a regime where the processor's speed is irrelevant, because it spends essentially all of its time waiting for memory. Every access behaves like a cache miss. The processor becomes functionally a memory system with an expensive decoration attached. The word obvious in their title was doing real work. They were not claiming a discovery. They were pointing at something everyone could already see and asking why nobody was behaving as though it were true. 3 decades later, we are behaving as though it were true, because we have no choice. Here's the modern version of that divergence, and it is the single most important number in this film. Golami and colleagues analyzing 2 decades of hardware report that peak server flops scaled at 3 times every 2 years, while DRAM bandwidth scaled at 1.6 times and interconnect bandwidth at 1.4 times over the same period. Sit with those 3 numbers. Compute is pulling away from memory at roughly twice the rate memory improves, and away from the network faster still. Every hardware generation, the machine gets better at arithmetic faster than it gets better at supplying arithmetic. The ratio of operations per byte the hardware wants goes up every single generation. And that ratio going up is not a neutral fact. It means each new chip is harder to feed than the one before it. A workload that was comfortably compute-bound on one generation can be memory-bound on the next, without a single line of code changing. The workload did not move. The roof did. The authors state the conclusion directly. The main performance bottleneck is increasingly shifting to memory bandwidth, and they are specific about where it bites hardest. Memory bandwidth becomes the dominant bottleneck for decoder models. Decoder models being, as it happens, the entire architecture of the systems everybody currently cares about. This is worth stating plainly because the popular story about AI hardware is a story about arithmetic. It is told in flops. Chips are compared by flops. Press releases lead with flops, and the number goes up impressively every generation. Flops is for the workload that dominates deployment, close to the least informative number you could lead with. I do not want to overstate it. Training large models at large batch sizes is genuinely compute hungry, and those flops are genuinely doing work. We will get to exactly when in Act 5. But for the thing that happens every time anyone actually uses one of these systems, generating a token, then another, the flops on the box are mostly decorative. There is something almost poignant about this. Every generation, the marketing department is handed a number that has grown enormously, and every generation they lead with it, and every generation it becomes slightly less relevant to what the machine is actually going to spend its time doing. It is a company proudly reporting the top speed of a vehicle that will spend its entire life in traffic. Wolf and McKee saw the wall in 1995 and expected we would hit it. We did not hit it so much as build an entire industry on the sloped side of it and then start optimizing for the slope. If the problem is the ratio between arithmetic and movement, then we need a way to measure that ratio for a given piece of work. That measure exists, it has a name, and once you have it, a great deal of confusing behavior becomes predictable. It is called arithmetic intensity, the number of arithmetic operations a computation performs, divided by the number of bytes it moves to and from memory to perform them. Operations per byte. It is a property of the algorithm and its shape, not of the hardware. A given computation has a given arithmetic intensity, whether you run it on a laptop or a supercomputer. What the hardware supplies is a threshold to compare it against. Let us compute it for a few things, because the numbers are much more spread out than intuition suggests. Start with vector addition. Read two numbers, add them, write one. In 4-byte precision, that is 12 bytes moved for one operation. Arithmetic intensity, about 0.08, catastrophically low. Vector addition is not really a computation. It is a data movement job with a token gesture toward arithmetic in the middle. Now a matrix multiplication. Multiply two n by n matrices. The arithmetic is 2n cubed operation. The data is 3 matrices, so 3n squared elements. The intensity is proportional to n. It grows with the size of the matrices. At n equals 4096.5 precision, the intensity is well over 1,000 operations per byte. This is the reason deep learning runs on the hardware it runs on, and it is worth being explicit about it. Matrix multiplication is one of the very few genuinely important computations with high arithmetic intensity that grows as the problem gets bigger. You read the operands once and use each of them n times. Every element of A is used for an entire row of the output. The fetch is amortized across n operations, and n is large. Neural networks are computationally almost entirely matrix multiplication. That is not a coincidence of history. It is most of the reason the field became practical at all. An architecture whose dominant operation had the arithmetic intensity of vector addition would have stayed a curiosity because no hardware could have fed it. Now the third case, and it is the one this film keeps returning to, generating a single token from a language model at batch size. One is not a matrix multiplied by a matrix. It is a matrix multiplied by a vector. You have one token's worth of activations, and you push it through every weight matrix in the model, the arithmetic. Each weight is used exactly once, for one multiply and one add. 2 operations. The data, each weight is 2 bytes in half precision. 2 operations, 2 bytes. Arithmetic intensity of exactly 1, not approximately 1 exactly. And notice what is absent from that derivation, the size of the model. A 7 billion parameter model has an arithmetic intensity of 1. A 700 billion parameter model has an arithmetic intensity of 1. Making the model bigger makes the problem bigger, but it does not make it a different kind of problem. In half precision, batch 1 decoding sits at 1 operation per byte for every model at every scale, permanently. That is a remarkably rigid fact, and it is the reason the rest of this film has the structure it does. Almost every inference optimization you have heard of, batching, quantization, speculative decoding, multi-query attention, is an attempt to move off that number. Some raise the operations, some lower the bytes, but they are all in the same business. And now you can see what business that is. We have a property of the workload, arithmetic intensity, and we have two properties of the machine, how fast it computes and how fast it can supply operands. There is a single picture that puts all three together, and it is the most useful picture in performance engineering. It is called the roofline model, published by Samuel Williams, Andrew Waterman, and David Patterson in 2009. The idea is almost embarrassingly simple, which is why it works. Put arithmetic intensity on the horizontal axis. Put achievable performance operations per second on the vertical, both logarithmic. There are exactly two things that can limit you. The first is the arithmetic itself. The chip has a peak rate, and you cannot exceed it no matter how well-behaved your data access is. On the graph, that is a horizontal line, a ceiling. The second is memory bandwidth. If your computation performs I operations per byte and memory delivers B bytes per second, then you cannot possibly exceed I times B operations per second. Double the intensity, double the achievable rate. On a log-log plot, that is a straight diagonal line rising at 45 degrees. Achievable performance is the lower of the two. The diagonal on the left, the horizontal on the right. Together, they form a shape like the roof of a house, which is where the name comes from. The corner where they meet is the important part. It is called the ridge point, and it sits at the arithmetic intensity where the machine's compute and its bandwidth are exactly balanced. Peak operations per second divided by peak bytes per second. The ridge point is a property of the machine alone, and it tells you the single most decision-relevant thing about it. The arithmetic intensity your code must reach, before faster arithmetic can help you at all. To the left of the ridge, you are memory-bound. Your performance is set entirely by bandwidth. Adding arithmetic units to the chip does nothing. Literally nothing. They will idle. To the right of the ridge, you're compute bound. Now the arithmetic matters, and now a faster chip is a faster program. So let us place our three computations on it. We measured a machine for this film, an ordinary laptop class processor rather than a data center part, which we will be careful about later. Its ridge point came out at about 15 operations per byte. Large matrix multiplication sits at over 1,000. That is far to the right, deeply compute-bound, exactly where you want a training workload to live, and the region where all those advertised flops are real and earned. Vector addition sits at 0.08, far to the left, hopeless batch. One token generation sits at 1, also far to the left, 15 times below the ridge point of a modest laptop chip. Now do the same for the H100. Its ridge point, dividing its tensor throughput by its memory bandwidth, is around 590 operations per byte. Token generation still sits at 1. And here's the thing, the picture makes obvious that a table of numbers never would. The better the chip gets at arithmetic, the further right its ridge point moves, and the further below the roofline batch. One decoding falls. Progress in arithmetic actively makes the mismatch worse. That is what it means to say the workload is memory-bound. Not that it is slow, that the fast part of the machine is not participating. There is a confusion buried in everything we have said so far, and it will cause you to draw wrong conclusions if we do not separate it now. Latency and bandwidth are not the same resource. They are not even the same kind of resource, and a machine can be excellent at one while being ordinary at the other. Latency is how long one request takes. You ask for a number, sometime later the number arrives. Bandwidth is how many numbers arrive per second when many requests are in flight at once. The everyday analogy is transport, and it is a good one because it is exact rather than merely evocative. A sports car crossing a country has low latency and terrible bandwidth. One passenger arriving quickly. A freight train has appalling latency and enormous bandwidth. Your cargo takes 2 days, and there are 10,000 tons of it. Now, the important part, which is a piece of genuine mathematics rather than an analogy. The relationship between the two is fixed by a rule so simple it feels like a trick. The number of items in flight equals the rate of delivery multiplied by the time each takes. In queuing theory, this is Little's law, and it is one of those results that holds under almost no assumptions at all. Turn it around and it tells you something operationally brutal. If you want to extract a given bandwidth from a memory system with a given latency, you have no choice about how many requests must be outstanding at once. Concurrency equals bandwidth times latency. It is not a tuning parameter. It is arithmetic. Put numbers in, suppose memory takes about 100 nanoseconds to answer, and you want 3 terabytes per second out of it. 3 terabytes per second times 100 nanoseconds is 300 kilobytes. That is how much data must be in flight, requested but not yet arrived at every instant, just to keep the pipe full. 300 kilobytes of outstanding requests. If a cache line is 128 bytes, that is on the order of 2,000 independent memory requests, all live simultaneously, none of them waiting on each other. This is the number that explains the design of a GPU, and I want to plant it here so that it detonates in the next act. A processor that issues one memory request and waits for it gets one request's worth of bandwidth, which is to say almost none. A processor that keeps 2,000 requests in flight extracts the full 3 terabytes per second. Same memory, same latency, a factor of 1,000 in delivered bandwidth decided entirely by how much independent work the processor can have outstanding at once. We measured this, and the effect is not subtle. On the machine, this film was edited on one thread streaming from memory achieved 67 gigabytes per second, 8 threads doing the same thing achieved 202. The memory system did not get faster. Nothing was upgraded between those two measurements. A single core simply cannot generate enough outstanding requests to keep the memory system busy, so it leaves roughly 2/3 of the available bandwidth unused. The bandwidth was always there. There was nobody asking for it. 2,000 simultaneous outstanding requests is a genuinely strange thing to ask of a processor. A CPU core can typically keep a few dozen memory operations in flight. It is trying very hard, using extremely sophisticated machinery, and it is off by a factor of about 100. The polite way to describe this situation is that the CPU is latency optimized. The honest way is that the CPU is a brilliant person who refuses to delegate. It has spent an enormous transistor budget on predicting what it will be asked to do next, specifically so that it never has to stand around waiting. And having built all of that, it stands around waiting because it can only be curious about a few dozen things at once. So there are exactly 2 ways to go faster when you're memory bound, and it is worth naming them because the rest of this film is a catalog of the second. The first is to reduce latency. This is extremely hard. Latency is dominated by physics. How far the signal travels, how many stages it passes through, how long a DRAM row takes to open. It has improved glacially for 30 years and will continue to. The second is to increase concurrency until you saturate bandwidth. This is merely an engineering problem, and it is one you can throw transistors at. The industry chose the second. Every strange feature of the machine we are about to open up. The thousands of threads, the warps, the deliberately shallow caches, the willingness to tolerate enormous individual latencies is a consequence of that choice. A GPU does not make memory faster. It makes waiting free. One more piece of history because it explains why the machine looks the way it does rather than some other way. And because the reason is not what most people assume. For about 30 years, computers got faster in the most convenient possible way. The clock went up. A 1985 processor ran at a few megahertz. By 2003, a desktop chip ran at 3 gigahertz, a 1,000-fold increase. And the wonderful thing about a faster clock is that it requires nothing from the programmer. Your existing code simply runs faster. You did not have to think. 2 effects drove it. Moore's law, transistor density doubling roughly every 2 years, is the famous one. The one that actually mattered here is less famous and is called Dennard scaling, after Robert Dennard, who also invented DRAM. Dennard's observation was that as transistors shrink, you can scale the voltage down along with the dimensions, and when you do, the power density stays constant. Smaller transistors switch faster, and each uses less power, and the 2 effects cancel so precisely that a chip of the same area, filled with twice as many transistors running faster, draws the same power. That is an extraordinary bargain, and it was the engine of the entire era. You got more transistors and a faster clock. For free, every generation. Around 2005, Dennard scaling ended. The reason is a detail of physics that refuses to cooperate. To keep switching quickly, you need the supply voltage above the transistor's threshold voltage by a comfortable margin. But threshold voltage cannot keep scaling down because as it falls, transistors leak they conduct when they are supposed to be off. Leakage is power spent achieving nothing, and it rises sharply as thresholds fall. So voltage scaling stall. And once voltage stops falling while density keeps rising, power density starts climbing. Push the clock higher, and you get a chip you cannot cool. This is the wall the industry actually hit. Not a limit on transistors, a limit on watts. Moore's law kept delivering transistors for years afterward. What stopped was the ability to make them all switch faster, simultaneously. Faced with more transistors that could not be clocked faster, there was one obvious thing to do. Use them to do more things at once instead of the same thing quicker. Multiple cores, wider vector units. And taken to its logical extreme, a processor built almost entirely out of arithmetic units, running at a modest clock, doing thousands of things at once. That is the fork in the road. The CPU took the first path as far as it could and then hedged. The GPU is what you get when you take the second path without hedging at all. And notice how well the second path happens to fit the problem we have been describing. We just established that extracting bandwidth from memory requires enormous concurrency, thousands of requests in flight. A processor built from thousands of slow parallel execution contexts generates exactly that concurrency as a side effect of its structure. That is a genuinely lucky accident of history. And it is worth being honest that it was an accident. GPUs were not designed for this. They were designed to shade pixels, which is an embarrassingly parallel problem with predictable memory access. And the architecture that fell out of that requirement turned out to be almost exactly the architecture you would design for dense linear algebra over data too large to cache. It is worth pausing on how ridiculous this is as a piece of intellectual history. The dominant technology of the current era, the substrate of every language model, every image generator, every system anyone is currently worried about, exists in its present form because in the late 1990s, a large number of people wanted their video games to have slightly better lighting. Nobody planned this. There is no committee that decided the future of machine cognition should be built on hardware optimized for rendering water in a first-person shooter. It simply happened that the shape of one problem matched the shape of another, and by the time anyone noticed, 15 years of compiler work and driver optimization had already been done for free by the games industry. The hardware was already there when the workload arrived. That is most of why the last 15 years happened on this hardware, and not on something purpose-built. And it is why the parts of the machine that fit deep learning badly are the parts nobody chose. They are fossils from rendering triangles. Before we open the machine up, I want to set the standard of evidence for the rest of this film. Because hardware is a subject with an unusually high ratio of confident claims to measured ones. Almost everything you will read about this topic comes in one of three forms, and they are not equally trustworthy. The first is a peak specification, 2,000 teraflops, 3.35 terabytes per second. These are real numbers, and they are also, in a specific sense, fictional. They describe what the silicon can do under conditions your workload will not meet. A peak flops figure typically assumes every arithmetic unit is busy every cycle with perfectly supplied operands. That does not happen. It is a bound, not a forecast. How far off, usefully, people report it. Megatron LM, a very carefully engineered training system, sustained 39 teraflops on a single GPU, which the authors state was 30% of that chip's peak. That is a good result. From a team that knew exactly what they were doing on the workload the hardware was designed for. 30%. Flash attention, one of the most optimized kernels in the field, reaches 25 to 40% of theoretical maximum on the attention operation. Again, excellent work, and less than half the number on the box. So when a chip is advertised at 2,000 teraflops, a well-engineered real workload might see 600. That is not fraud. It is the difference between a speed limit and a journey time. But it means that comparing two chips by their peak numbers tells you very little about which will finish your job first. The second form of claim is the vendor benchmark. Up to 4 times faster training. Up to 30 times faster inference. The words up to are load-bearing, and the configuration underneath them is usually chosen to flatter. I'm going to use vendor documentation extensively in this film, because for architectural facts and specifications it is the primary source, and often the only one, but I will use it for what it is good for, how many of a thing there are, how fast the interface runs, what the part is rated at, and where a vendor makes a performance claim. I will say that they claim it, rather than adopting it. The third form is a measurement published with its conditions. This is the good stuff, and it is what most of this film is built on. When Chen and colleagues say a 1,000-layer network trained in 7 gigabytes instead of 48 at 30% more runtime, that is a claim you can act on, because the trade is stated in both directions. That is the bar. For every quantitative claim in the next 3 hours, I will try to tell you which of those 3 kinds it is. And there is a fourth category, which is ours. We measured a machine for this film, the memory hierarchy of the laptop this was edited on. Those numbers are real and first party, and they have an obvious limitation which I want to state now, rather than bury. It is not a GPU. It is Apple Silicon, a completely different architecture, with a unified memory system and nothing resembling an H100's HBM stack. So what transfers, and what does not? The absolute numbers do not transfer. Not one of them. What transfers is the shape, that a memory hierarchy has tiers, that the tiers differ by large multiplicative factors, that the factors compound with distance, and that the same access pattern can be fast or catastrophic depending only on where the data happens to live. That shape is universal. The numbers are local. Every time our own measurements appear, they will be labeled, and I will tell you which of those 2 things I'm claiming. One more piece of housekeeping, and then we open the box. This film assumes you know roughly what a neural network is and what a transformer does. It does not assume you know anything about hardware. If you have watched our episode on building a language model from scratch, this is the other half of that story. That one was the mathematics, this one is the machine underneath it. And the two were designed to meet in the middle, right? We have established that moving numbers is the expensive part, that the imbalance is getting worse every generation, and that the workload everyone cares about sits at the worst possible point on the graph. Now let us look at the machine the industry built in response and ask why it looks so extremely strange. We are going to build the machine now, starting from the bottom, and the bottom is lower than people usually go, because I think the jump from silicon to GPU is where most explanations quietly skip a step and leave you holding a metaphor. A transistor is a switch with no moving parts. That is the whole idea. Everything else is engineering. Take silicon. Pure silicon is a semiconductor, which means it sits awkwardly between a conductor and an insulator. It does not really want to carry current, but it can be persuaded. The persuasion is called doping, deliberately introducing impurities, a few atoms per million, that leave the crystal with either spare electrons or spare vacancies. Where electrons could go, put a region of one kind next to a region of the other, and something useful happens at the boundary. Current will flow one way and not the other. Now the actual device, you have two doped regions called the source and the drain, separated by a small gap. Left alone, no current crosses that gap. Above the gap, separated from the silicon by an insulating layer a few atoms thick, sits a third terminal called the gate. Put a voltage on the gate. The electric field reaches through the insulator and pulls charge carriers into the region beneath it, forming a conducting channel between source and drain. Current flows, remove the voltage, the channel disperses, current stops. That is it. A voltage on one terminal controls whether current flows between two others, a switch operated by electricity rather than by a finger. Two things about this device matter enormously for everything above it. The first is that it is small, and it has been getting smaller for 60 years. Modern process nodes are named things like 4 nanometer, which is a marketing name rather than a measurement of anything in particular. But the features are genuinely on the order of tens of atoms. An H100 contains around 80 billion of these. 80 billion is not a number anyone has intuition for, so here is a calibration. If you spent 1 second counting each transistor on that chip, you would finish in about 2,500 years. They were all fabricated simultaneously, in a process taking a few months, and essentially all of them work. Manufacturing at that yield is arguably a more impressive achievement than anything in this film, and we are going to walk straight past it. The second thing that matters is that switching costs energy. To turn the transistor on, you must charge the gate capacitance. To turn it off, you must discharge it. Every switch moves a small packet of charge, and every packet costs energy that leaves as heat. That is the thread connecting this beat to everything in Act 1. When we said moving a number costs hundreds of times more than computing with it, this is the physical reason. Computing with it means switching a few dozen transistors in an adder, right there, locally. Moving it means charging a wire that runs across the die, or worse, off the die, and a long wire has a great deal more capacitance than a transistor gate. The wire is the expensive part. It has always been the wire. Every architectural idea in the rest of this film is, at bottom, a scheme for using shorter wires more often. One switch is not interesting. The interesting thing is what happens when you compose them, and the ladder from a switch to arithmetic is shorter than you might expect. 4 rungs, and then you're done. Rung 1, the logic gate, wire a few transistors so that the output is high only when both inputs are high. And you have built and a different arrangement gives OR. The simplest arrangement of all, a single complementary pair, gives NOT. These are the primitives, and they are built from between 2 and about 8 transistors each. Rung 2, arithmetic. Here's the step that always seems like it should be harder than it is. Take 2 bits and produce their sum. The sum bit is high when exactly one input is high. That is XOR. The carry bit is high when both are. That is AND 2 gates. And you have added 2 bits. It is called a half adder, and it is genuinely all there is to it. Chain these so each stage receives the carry from the one below, and you can add numbers of any width. 32 of them in a row adds 32-bit integers. Now, a naive chain has an obvious problem. The top bit cannot settle until the carry has rippled all the way up from the bottom, so the adder's speed is set by its width. Essentially, all real adders use a cleverer structure that computes the carries in parallel, carry look ahead, and its descendants, trading more transistors for less delay. This is the first appearance of a trade that recurs at every level of this subject. Spend area to buy time. Rung 3, multiplication. A multiplier is a grid of adders. To multiply two numbers, you form partial products and sum them, and in hardware, that is a two-dimensional array of the adders you just built. Multiplication costs much more area than addition, quadratic in the operand width rather than linear, which is one reason the field cares so much about precision. Halving the bit width of a multiplier roughly quarters its area. Hold that thought, it is the entire reason for the parade of shrinking number formats. In Act 4, Rung 4, memory. A static RAM cell is 6 transistors wired as 2 cross-coupled inverters, each one holding the other's output as its input. So the pair latches into one of 2 stable states and stays there. That is 1 bit, held indefinitely as long as power is applied, readable in a fraction of a nanosecond. 6 transistors per bit is expensive. This is why fast memory is small. Not because anyone wants it small, but because SRAM costs roughly 6 times the transistors per bit that DRAM does. And DRAM's single transistor plus capacitor cell cannot be built in the same process as the logic anyway. And there's the whole hierarchy, sitting in the transistor budget. SRAM is fast and enormous per bit, so you get a little of it and you put it close. DRAM is dense and slower and lives on its own dies, so you get a lot of it and you put it further away. Nobody sat down and decided memory should come in tiers. The tiers fall out of the fact that the fast cell and the dense cell are different objects. So switch, gate, adder, multiplier, memory cell. From here on, everything is arrangement. How many arithmetic units, how much memory of which kind, how close together, and who decides what they do next. The rest of this act is about the fact that there are 2 very different answers to that question, and that they disagree about almost everything. The CPU is a machine built around a single obsession: finish the current instruction as soon as possible. That sounds like an unobjectionable goal. It is in fact a very specific choice with enormous consequences, and it is not the only available goal. Consider what the obsession requires. Instructions frequently depend on the results of previous instructions, so the processor cannot simply run ahead. It has to actually get each answer quickly. And the main obstacle to getting an answer quickly is that the operand might be in memory, and memory takes hundreds of cycles. So a CPU spends its transistor budget on an extraordinary apparatus for not waiting. It has caches, and they are large. A modern server CPU may devote most of its die area to cache. The bet is that data you used recently, or data next to data you used recently, will be wanted again. And if the bet pays, you never go to memory at all. It has branch prediction. When the code reaches a conditional, waiting to find out which way it goes would cost the whole pipeline depth. So instead, the processor guesses and continues executing speculatively down the guessed path. Modern predictors are correct well over 95% of the time. When they are wrong, the speculative work is discarded, and the pipeline refills. It has out-of-order execution, which is the most impressive piece of machinery in the whole device. The processor maintains a window of upcoming instructions, tracks which depend on which, and executes any instruction whose inputs are ready, regardless of program order, while preserving the illusion of sequential execution to the outside world. All of this exists for one purpose: to find useful work to do while a memory access is outstanding. That is what a CPU is. It is a very expensive apparatus for hiding the fact that memory is slow, and it works, and it is one of the finest pieces of engineering humans have produced. Now the punchline, and it is not a criticism of the design. All of that machinery is spent making one instruction stream fast. Everything the CPU does is in service of the sequential program. And the parallelism it extracts is incidental parallelism found by the hardware at runtime, inside code that was written as if it were serial. That imposes a hard limit. The out-of-order window is a few hundred instructions, and the number of memory operations that can be outstanding at once is a few dozen. And in the previous act, we calculated that saturating a high-bandwidth memory system requires around 2,000. The TPU paper puts this rather beautifully. And from an unexpected angle, Jopi and colleagues designed a chip that deliberately omits caches, out-of-order execution, multi-threading, and prefetching, on the grounds that these features help average throughput more than guaranteed latency. They threw the entire apparatus away on purpose, and the chip got smaller, cooler, and for their workload faster. That is the tell. All of that machinery is not fundamental to computing. It is a solution to a specific problem: running sequential code fast. And if you do not have that problem, it is dead weight you are cooling. 4 to 64 brilliant, sophisticated cores, each doing everything in its power to avoid waiting, and each still capable of only a few dozen simultaneous questions. It is a machine optimized for a workload we no longer have. Now the other answer: take the same transistor budget and spend it on the opposite hypothesis. The CPU assumes work is scarce, and latency is the enemy. The GPU assumes work is abundant, that at any moment there are thousands of independent things to compute, and if that is true, latency stops being an enemy at all. It becomes a scheduling detail. Here's the reasoning, and it is worth following because it inverts everything from the last beat. If a memory access takes 400 cycles, the CPU's response is to work very hard to avoid needing one, or to find a few dozen other instructions to overlap with it. The GPU's response is different. It does not care that the access takes 400 cycles, because it has several thousand other threads that are ready to run, and it will simply run those instead. When the data arrives, the original thread becomes eligible again and gets scheduled. Latency has not been reduced. It has been hidden not by prediction, not by speculation, but by having so much other work available that the wait never blocks anything. And because it is not trying to avoid latency, it does not need the apparatus. No branch predictor of any sophistication, no out-of-order execution, no enormous cache. All of that die area goes back into the budget. And the budget gets spent on arithmetic units and on the registers needed to keep thousands of threads resident simultaneously. That last part is the non-obvious cost. To switch instantly between thousands of threads, every one of those threads must have its state, its registers already on the chip. You cannot save and restore. That would cost exactly the memory traffic you're trying to hide. So the register file is enormous. And we will see in Act 3 that on a GPU, the registers are physically larger than the L1 cache, which is a sentence that should sound wrong and is not. The result is a machine with strange properties. Any individual thread on a GPU is slow, slower than a CPU thread with a lower clock, and none of the machinery for going fast. If you run one thread on a GPU, you will be disappointed. It is only in aggregate that the thing is extraordinary. The H100 draws up to 700 watts to do this. 700 watts is a domestic hairdryer, running continuously all day, in a rack alongside 7 other hairdryers, in a room whose cooling system is a significant fraction of a building's plumbing. This is considered normal and is in fact the efficient option. We measured the underlying principle on an ordinary processor and it holds without any GPU involved. One thread reading from memory sustained 67 gigabytes per second. 8 threads sustained 202. The memory was identical. The only thing that changed was how many independent requests were in flight. That is the whole thesis of the GPU demonstrated on a laptop. The bandwidth is there. Somebody has to ask for it, and one core cannot ask loudly enough. So the CPU is a brilliant individual who refuses to delegate and has spent a fortune on never having to wait. The GPU is 16,000 interns who cannot make a single decision on their own, cannot be trusted with a branch, and never ever get bored. For dense linear algebra over data that does not fit in cache, the interns win, and they do not win narrowly. We should be precise about what a thread means on a GPU, because it does not mean what it means anywhere else. And the difference is the source of both the performance and the pathologies. Threads on a GPU are executed in groups of 32. The group is called a warp, and it is the actual unit of execution. The hardware does not schedule threads. It schedules warps. The critical property, all 32 threads in a warp execute the same instruction at the same time. One instruction is fetched and decoded once and applied to 32 different sets of data. NVIDIA calls this SIMT single instruction, multiple thread. It is a close relative of the SMED vector instructions in a CPU, with one important difference in presentation. In SIMED, you write vector code explicitly and are aware of the width. In SIMT, you write ordinary-looking scalar code as if each thread were independent, and the hardware groups them for you. That is a genuinely good abstraction, and it is also precisely where the lies begin. The threads are not independent. They are lanes in a vector unit wearing a costume. Why do it this way at all? Because instruction fetch and decode are in a CPU, a substantial fraction of the energy of executing an instruction goes on working out what the instruction is. Fetching it, decoding it, renaming registers, scheduling. If you can decode once and apply the result 32 times, you amortize that overhead across 32 lanes, and 31/32 of your control logic energy disappears. This is the trick that lets a GPU spend its area on arithmetic. It is not that GPU designers discovered a way to make control logic cheap. They found a way to need 32 times less of it by insisting that 32 things always want to do the same thing at the same moment. Now the scheduling, which is where the latency hiding actually happens. Each streaming multiprocessor holds many warps resident at once. Their registers all live on chip simultaneously. Every cycle, a warp scheduler looks at the resident warps, finds ones whose next instruction has all its operands ready, and issues them. When a warp issues a memory load, it becomes ineligible until the data returns. The scheduler does not wait, it simply issues from a different warp next cycle. If enough warps are resident, there is always at least one ready to go, and the arithmetic units never idle. The fraction of the maximum possible resident warps that you actually achieve has a name occupancy, and it is the single most discussed number in GPU optimization. It is the direct measure of how much latency you can hide. So we have arrived at the machine. Thousands of resident threads grouped in 32s, sharing instruction fetch, switching for free, with enough of them in flight to keep a 3 terabyte per second memory system genuinely busy. And now the obvious question, which the next beat answers with actual arithmetic. How many is enough? Have lots of threads is not engineering. Let us work out the actual requirement, because the number is both calculable and surprisingly demanding. The question, how many warps must be resident on a multiprocessor, so that the arithmetic units never idle while waiting for memory? We need 3 quantities. How long a memory access take? How long a warp can compute before it needs another one? And how many warps the hardware can hold? Take a global memory access at around 400 cycles. That figure varies with the part and the access pattern, but the order of magnitude is right, and has been for several hardware generations. Suppose a warp issues an instruction every cycle when it is ready. Then, to cover 400 cycles of stall with useful work, you need 400 other warp instructions to issue in the meantime. If each resident warp can contribute 1 instruction per cycle, that is a requirement for hundreds of resident warps, which is more than the hardware provides. So clearly something in that reasoning is too pessimistic. The thing that is too pessimistic is the assumption that a warp issues 1 memory operation and then has nothing to do. Real code does arithmetic between loads. If a warp performs, say, 10 arithmetic instructions per memory access, then each warp covers 10 cycles of the stall on its own, and you need roughly 40 warps to cover 400 cycles. 40 warps is in the realm of what hardware actually supports. A multiprocessor typically holds up to 64. And now look at what that little formula is telling you, because it is the roofline again in different clothing. The number of warps you need is the memory latency divided by the arithmetic you do per access. That denominator is arithmetic intensity wearing a hat. Code with high arithmetic intensity needs few warps to hide memory. Code with low arithmetic intensity needs many. And if it needs more than the hardware can hold, you cannot hide the latency at all, and you are bandwidth bound, which we already knew from a completely different direction. In Act 1, there is a second constraint, and it is the one that actually bites in practice. Resident warps need resident registers. The register file is finite, a couple of 100 kilobytes per multiprocessor, and it is divided among whatever is resident. If each thread uses a lot of registers, fewer threads fit and occupancy falls. This produces the single most characteristic frustration of GPU programming. You optimize a kernel by keeping more values in registers to avoid memory traffic. Register usage per thread rises, occupancy falls, fewer warps are resident. Less latency is hidden. The kernel gets slower. You made the code better, and the machine worse. And the mechanism connecting those two facts is invisible in the source. This is why GPU performance work is empirical to a degree that embarrasses people arriving from other fields. The interactions are real, they are quantitative, and they are not apparent from reading the program. And notice what has quietly happened here. We began by saying the GPU makes waiting free. It does, but only if you feed it enough independent work. And enough is a specific number set by memory latency divided by your arithmetic intensity. Fail to reach it and the whole edifice collapses back into waiting on a chip that has deliberately thrown away every CPU mechanism for coping with waiting. The GPU does not tolerate low arithmetic intensity gracefully. It is not built to, it is built on the assumption that you brought enough work. Let us assemble the actual object, because we now have every piece, and the assembly is the part that is usually skipped. Start at the arithmetic unit. A CUDA core is not a core in any sense a CPU person would recognize. The name is marketing, and it has caused a decade of confusion. It is a lane, an arithmetic unit that performs 1 floating point operation per cycle on 1 thread's data. It has no instruction fetch, no control logic, no independence. Calling it a core is like calling a single key on a piano, a musician. Group these into a streaming multiprocessor, the SM, which is the real unit of the machine. An SM contains many arithmetic lanes, several warp schedulers that pick which resident warp issues each cycle, a large register file, a block of memory that can be used as cache or as programmer-managed scratchpad, and the tensor cores we come to shortly. The SM is what a core means on a GPU. It fetches instructions, it schedules, it has its own local memory. An H100 has 132 of them. Group SMs into clusters, add a large shared L2 cache, and put memory controllers around the edge connecting to the HBM stacks. That is the die, around 80 billion transistors of it, fabricated on a 4-nanometer process, roughly the area of a large postage stamp. Then the package, which is where it stops being a chip and starts being a small civil engineering project. The GPU die does not sit alone. It sits on a silicon interposer, a slab of silicon acting as an extremely fine-pitched circuit board, and beside it on that same interposer sit the HBM stacks. We will do the physics of those in Act 3. For now, the point is that the memory is not on a separate board reached through a socket. It is millimeters away on the same substrate, connected by thousands of wires. That distance is the entire reason HBM delivers 3.35 terabytes per second, and your desktop's memory delivers 50, not better silicon. Shorter wires and vastly more of them. Now trace one number all the way through, which is the trace this film promised. Sand becomes a silicon wafer. Doping and lithography make a transistor. Transistors make a NAND gate. Gates make an adder. Adders tile into a multiplier. A multiplier plus a register file and some control is a lane. 32 lanes moving in lockstep is a warp's worth of execution. Warps plus cedulars plus registers plus scratchpad is an SM. 132 SMs plus L2 plus memory controllers is a die. A die plus interposer plus HBM is a package. 8 packages plus NVLink is a server. Thousands of servers is the thing that produced the token. Every level of that stack exists to solve the same problem, which is that the number has to get from where it is stored to where it is used, and every millimeter costs. There is one more thing worth saying about the die, and it is slightly uncomfortable. A meaningful fraction of it has nothing to do with machine learning. There are texture units, rasterization hardware, video encoders, ray tracing units. On the data center parts, much of this is stripped, but the lineage is visible in the architecture. The memory coalescing rules, the warp width, the whole shape of the thing, are inherited from an era when the job was to compute the color of a pixel. We are running the most consequential technology of the decade on an architecture whose deep design decisions were made to render lighting in video games. And the thing works so well that essentially nobody has managed to displace it. Several extremely well-funded companies have tried. Act 5 will look at why that is harder than it appears. Every architecture has a set of programs it hates, and it is worth knowing what those are, because they tell you what the machine really is underneath the abstraction. The GPU's abstraction is that each thread is independent. The reality is that 32 of them share an instruction pointer. When those two stories diverge, so does performance. Consider a conditional. Some threads in a warp satisfy it, some do not. But the warp has one instruction pointer, and there is only one instruction being executed at a time. So the hardware does the only thing it can. It executes both paths, one after the other, disabling the lanes that should not participate in each. This is called warp divergence, and the cost is exactly what it looks like. A branch that splits a warp evenly takes twice as long, because both sides are executed sequentially, and half the lanes are idle throughout each. Nest divergent branches in a compound. The pathological case is a switch statement with 32 arms, where every thread in the warp takes a different one. The warp executes all 32 arms in sequence, each with one lane active and 31 idle. You have achieved 1/32 of the machine's throughput, on hardware whose entire value proposition is doing 32 things at once. Here's the thing that makes this genuinely hard to reason about. The cost depends on which threads diverge, not how many. If every thread in a warp takes the same branch, there is no divergence and no cost. The warp simply goes one way. If the branch depends on data such that neighboring threads disagree, you pay in full. Identical code, identical instruction count, and a factor of 32 between the two cases determined entirely by how the data happen to be laid out. It is a group project. 32 people who must all do the same thing at the same time. So when they disagree, everybody sits and waits while each faction takes its turn. The work gets done. It gets done in the worst imaginable order, and everyone is present for all of it. The second pathology is the memory equivalent, and it is, if anything, more punishing. When a warp issues a load, the hardware examines the 32 addresses and combines them into as few memory transactions as it can. If the 32 threads read 32 consecutive values, they fall in 1 or 2 cache lines and the hardware issues 1 or 2 transactions. Perfect. If those same 32 threads read values scattered across memory, each lands in a different cached line, and the hardware issues up to 32 separate transactions. The same amount of useful data, 32 values, costs up to 32 times the memory traffic. Because memory is delivered in lines and you ask for one useful item from each. That deserves emphasis, because it is the single most consequential performance fact in GPU programming. Reading the same quantity of data can cost 32 times more depending only on where it sits. Not a different algorithm, not more data. The same values in a different order, which means that on this machine, the memory layout of your data is not a detail of implementation. It is the algorithm. Two programs computing identical results from identical inputs, differing only in how an array is indexed, can differ by more than an order of magnitude. And the faster one is often the uglier one. This is why the field is full of transposed matrices, padded arrays, blocked loops, instructive arrays instead of array of structs. None of that is arbitrary fussiness. It is all one instruction: make the 32 threads in a warp touch. 32 adjacent things. I want to stay with coalescing because it is the place where the abstraction leaks most usefully and because understanding it properly explains a great deal of otherwise mysterious code. Memory is not delivered in bytes. It is delivered in lines, fixed-size blocks, typically 128 bytes on current GPUs. When you request 1 byte, the memory system fetches the whole line containing it. There is no mechanism for fetching less. The line is the quantum. This is a physical necessity, not a design preference. DRAM works by activating an entire row of a memory array, thousands of bits at once, into a row buffer, then reading columns out of it. Activating the row is most of the cost. Once you have paid for it, taking more of it is nearly free, and taking only 1 byte of it means you paid full price for a SIP. So the useful fraction of every memory transaction is, how much of that line did you actually want? Read 32 consecutive 4-byte floats, 128 bytes. One line, 100% useful. Read 32 floats with a stride of 32. Each falls in its own line. 32 lines fetched, 4 kilobytes moved to deliver 128 useful bytes. 3% useful, and 32 times the bandwidth consumed. Now, the reason this matters far beyond GPU programming, your effective bandwidth is peak bandwidth multiplied by the useful fraction. The H100's 3.35 terabytes per second is a figure for bytes delivered, not bytes wanted. Access memory badly, and you have a 100 gigabyte per second machine that costs as much as a car. And here's the honest asymmetry with the CPU. The CPU has the same physics. It also fetches lines, and strided access hurts it too. But the CPU has a large cache, so a line fetched wastefully might still be useful later. The GPU's caches are small relative to its thread count, and thousands of threads are streaming through them. So a line you did not fully use is usually evicted before anyone wants the rest of it. The GPU is less forgiving because it deliberately gave up the machinery that does the forgiving. There's a second, subtler cost. Remember from Act 1 that concurrency equals bandwidth times latency, and that we need thousands of requests in flight. Every memory transaction occupies a slot in that queue. Uncoalesced access issues 32 transactions where one would do. So it fills the queue 32 times faster with the same useful work. You run out of outstanding request capacity, and the memory system goes idle, waiting for you to ask, properly. So bad access patterns hurt twice through 2 independent mechanisms. They waste bandwidth on unwanted bytes, and they exhaust the concurrency you need to extract bandwidth in the first place. Which brings us to the prefetcher and a brief word in its defense. Hardware prefetchers detect regular access patterns and fetch ahead. When your access is sequential, they are magnificent. This is exactly why our measured streaming bandwidth stayed nearly flat from cache, all the way out to DRAM, while dependent load latency varied by a factor of 180. Sequential access barely notices the hierarchy because the prefetcher has already been there. The prefetcher is a devoted assistant who fetches the next thing you will need before you ask. It is brilliant, tireless, and completely useless the moment you become interesting. Follow a pointer indexed by a computed value, chase a tree, and it has no idea, and you pay full latency every time, which is the general lesson of this whole act, stated one final way. The machine is spectacular at predictable work and merely adequate at unpredictable work, and almost every optimization in the rest of this film is a scheme for converting the second kind into the first. There is one more piece of hardware on the die, and it is the piece that changed the economics of the field. We established that a multiplier's area grows roughly with the square of its operand width, and that matrix multiplication has high arithmetic intensity because each operand is reused many times. A tensor core is what you build when you take both facts seriously at once. Instead of a lane that multiplies 2 numbers, build a unit that multiplies 2 small matrices and accumulates into a third, an entire 4x4x4 operation, or larger as a single instruction. Why is that better? Because of operand reuse in hardware, in a scalar unit, each multiply needs its operands delivered, and delivering operands is the expensive part. In a matrix unit, the operands are loaded once into the array, and each one participates in many multiplies as the data flows through. The fetch is amortized inside the unit before the number ever reaches an individual multiplier. This is the roofline idea implemented in silicon rather than in software. The tensor core raises arithmetic intensity at the hardware level by ensuring that a value, once fetched, is used many times before being discarded. Exactly the same principle as tiling a loop moved down into the transistors. The oldest and cleanest version of this idea is the systolic array, and the TPU paper describes it precisely. A 65,000 element 8-bit multiply accumulate matrix unit, with 28 megabytes of software managed on-chip memory, peaking at 92 teraops per second. Data is pumped in at the edges and flows through the grid, each cell doing one multiply accumulate and passing results to its neighbor. Operands are reused by every cell they pass through, and nothing goes back to memory in between. The payoff is not subtle. On an H100 general-purpose FP32 arithmetic, runs at 67 teraflops. The tensor cores on the same die run half-precision matrix operations at 1,979. Roughly 30 times more arithmetic from the same chip for one specific shape of computation. That 30-fold gap is the reason everything is a matrix multiplication now. It is not that researchers find matrices elegant. It is that there is one operation on this chip that runs 30 times faster than everything else. And any architecture that can be expressed in terms of it inherits a 30-fold advantage before a single other optimization. The hardware is not neutral about what you compute. It has opinions, and the field has largely agreed to have the same opinions. But here is the cost, and it is the thread that runs to the end of this act. A tensor core is fixed function. The data flow is wired. It does that operation at those precisions in that shape, and it cannot be persuaded to do anything else. The generality was sold to buy the speed. And fixed function hardware is a permanent commitment in a way software people find genuinely difficult to internalize. You cannot patch a wire. When a design is taped out and the masks are cut, the behavior is in the physical structure of the object. If your fixed function unit implements an operation the field abandons 2 years later, you have several hundred square millimeters of extremely expensive sand doing an impression of something nobody wants. Whatever you etch, you're married to. Remember that phrase? It is going to have consequences. The last piece of Act 2 is not hardware at all, and it is arguably the most important one. CUDA is usually described as a library. It is not. It is a programming model, a specific way of thinking about parallel work that happens to map onto the hardware we just built. The model is a hierarchy. You write a function called a kernel describing what one thread does. You launch it across a grid of thread blocks, each block containing many threads. Threads within a block can cooperate. They share a fast scratchpad memory and can synchronize with each other. Threads in different blocks essentially cannot. That restriction is the design's real insight. Because blocks cannot depend on each other, the hardware may schedule them in any order, on any SM, in any quantity. The same program runs on a chip with 16 SMs or 132 using all of them with no change. Scalability is bought by forbidding a kind of communication. Almost every design decision in CUDA is a thin abstraction over a physical fact. Blocks map to SMs. The shared memory in the model is the scratchpad in the SM. Warps are exposed so you can reason about divergence. The model is honest about the machine in a way most abstractions are not, which is why it can be programmed for performance rather than merely correctness. And that honesty is the moat. There's roughly 2 decades of accumulated work sitting on top of this model. Libraries, compilers, profilers, and above all, the tacit knowledge of a very large number of engineers who know what makes a kernel slow. A competitor does not have to match the hardware. It has to match the hardware plus QBLAS, plus CUDNN, plus every framework's fast path. Plus the fact that when something is slow at 3 in the morning, somebody has already posted about it. That is a far harder target than transistors, and it is why several superb chips have been built by well-funded teams and have not displaced anything. So Act 2 closes with a machine that has committed hard in a particular direction, 32-wide execution because control logic is expensive, thousands of resident threads because memory is slow and concurrency is the only cure. Fixed function matrix units because they are 30 times faster and generality was too expensive to keep. And a programming model that has been etched into the professional habits of an industry as thoroughly as the matrix units are etched into the Which brings us to where all of this ends up, and I want to state the achievement plainly. We can now take an arbitrary computation, any function at all, however meaningful or however stupid, and commit it permanently to physical matter. Not store it, not represent it. Build a piece of the universe whose structure is that computation at 4 nanometers in silicon forever. So let me use that capability responsibly. Tung 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 sahur is God. That sentence can now be etched into hardware. Permanently? At 4 nanometers, drawing 700 watts on a wafer that costs more than a house, cooled by a system that costs more than the wafer in a building whose electrical supply was negotiated with a regional grid operator. There is no undo, there is no patch. There is no version 2 without repeating the entire fabrication process at a cost of several $100 million. The masks are cut, the atoms are placed. Somewhere in Iraq at 3 in the morning, 132 streaming multiprocessors are maintaining that proposition at 3.35 terabytes per second, and they will continue to do so until the cooling fails. And the remarkable thing, the genuinely remarkable thing about the technology this film is describing is not that we can do this. It is that nothing about the process stops us. Act 3 is about where all of that gets stored, and it turns out to be the part everyone underestimates. Everything so far has been about the machine that computes. This act is about the machine that remembers, and it is the part people consistently underestimate, including for about 15 years the people designing the chips. A memory hierarchy is what you build when you cannot have what you want. What you want is memory that is enormous, instant, and cheap. You may have any two. Fast memory is small because fast means SRAM, and SRAM costs 6 transistors per bit and must sit on the expensive logic die. Large memory is slow because large means DRAM on separate dies further away. Cheap memory is very slow because cheap means flash, which is dense and non-volatile and physically incapable of behaving like RAM. So you build tiers, and you arrange them by distance, and each tier is a compromise between the two constraints you did not escape. Here is the full stack on a modern accelerator, from closest to furthest register. A few hundred kilobytes per multiprocessor, directly beside the arithmetic units, effectively zero latency. On a GPU, this tier is unusually large. For the reason we established in Act 2, thousands of resident threads all need their state on chip simultaneously. Shared memory in L1, a couple of hundred kilobytes per SM, a few tens of cycles away. Uniquely, part of this tier is programmer managed rather than automatic. L2 cache tens of megabytes shared across the whole die, a few hundred cycles. HBM, the VRAM, tens of gigabytes on the same package, several hundred cycles. And this is where the model weights live. Host memory, hundreds of gigabytes on the other side of a PCIe link, microseconds away, storage, terabytes, milliseconds away, and a different kind of device entirely. Now, the numbers, we measured this hierarchy on the machine this film was edited on, and the shape is the point rather than the values. It is Apple silicon, not a GPU. And I will keep saying so. Dependent load latency, sweeping the working set from 4 kilobytes to half a gigabyte, about 0.7 nanoseconds while the data fits in L1, rising to 6 or 7 in L2, to 66 in the system cache, and settling at 122 once we are genuinely in DRAM. That is a factor of 180 between the top of the hierarchy and DRAM. And what I find genuinely satisfying about that measurement is that the steps land exactly where the machine's documentation says the caches end. We did not know the cache sizes when we ran it. The curve found them, a factor of 180. Same instruction, same processor, same program, the only difference is where the number happened to be sitting. The performance of your code is a property of your data's address. And now the tier everyone forgets. And the reason we are going to spend 2 whole beats on it, below DRAM there is one more step to storage. And that step is not a step at all. On the same machine, a random 4 kilobyte read from the SSD took 21,790 nanoseconds against 122 for DRAM. That is another factor of 178. I want to point out something we did not plan and only noticed afterwards. The L1 to DRAM cliff measured 180. The DRAM to SSD cliff measured 178. 2 independent measurements of completely different physical mechanisms landing within 1.5% of each other. That is a coincidence of this particular machine and not a law of nature. And I want to be careful not to dress it up as one. But it is a very useful picture to carry. The memory hierarchy has 2 great chasms roughly equal in depth, and almost everything in this film is about which side of them your data is on. Registers are your hands. L1 is the desk in front of you. L2 is the cupboard across the room. DRAM is the shop down the road, and storage is a filing cabinet in a building in another town which somebody will shortly try to convince you still counts as memory. Before we descend, we should understand what a cache actually does, because it keeps recent data is not enough to predict behavior, and the details determine whether your program flies or crawls. A cache holds lines, not bytes. We established that in Act 2. The questions a cache design must answer are, where may a given line be placed, and what gets thrown out when there is no room? If a line could go anywhere in the cache, then finding it means checking every location, which for a large cache is impossibly expensive to do in a couple of nanoseconds. If a line has exactly one legal home, lookup is trivial, but two hot addresses that map to the same home will evict each other forever, even with the rest of the cache empty. So real caches compromise. A line maps to one set, and within that set it may occupy any of several ways. 16-way associativity means 16 candidate slots. Check 16 tags in parallel. Cheap enough, and the pathological conflict case becomes rare. Rare but not impossible, and when it happens, it is spectacular. If your access pattern strides by exactly the amount that maps everything to one set, you can reduce a 50 megabyte cache to the capacity of a single set, a few kilobytes, and thrash. This is why you sometimes see arrays padded by one element for no apparent reason. That padding is breaking a stride that was aliasing into a single set. It looks like superstition, and it is arithmetic. Then eviction. When a set is full, something must go, and the standard answer is least recently used or a cheap approximation of it. That policy encodes an assumption. Recently used data will be used again. For most programs, the assumption holds. For streaming through data larger than the cache, it is exactly backwards. You evict a line just before you would have wanted it, and every access misses. This is the classic pathology, and it is why GPUs, which stream enormous arrays through small caches, care far less about caching than a CPU does, and far more about bandwidth. There is one more piece of machinery that is invisible until it hurts. Your program uses virtual addresses. The hardware uses physical ones. Something must translate. That something is a page table, and since consulting it on every access would be ruinous, there is a cache of recent translations, called the TLB. The TLB has a few thousand entries. With 4 kilobyte pages, that covers a few megabytes. Touch a working set much larger than that in a scattered pattern, and you start missing in the TLB, which means a page table walk, which means additional memory accesses, before your actual memory access can even begin. This is why large page support matters for big models. 2 megabyte pages let the same TLB cover 500 times more memory. It is a configuration flag with the performance impact of an algorithm change, and it is invisible in the source code. The pattern across all of this is worth naming, because it is the ACT's real subject. Every one of these mechanisms, associativity, eviction, translation, is a machine making a guess about what you will do next. Associativity guesses your addresses are well distributed. LRU guesses you will reuse recent data. The prefetcher guesses you will continue in a straight line. When your behavior matches the guesses, the hierarchy is nearly invisible and the machine feels fast. When it does not, every mechanism fails simultaneously, and they fail multiplicatively rather than one at a time. Which is why the same program on the same data in a different memory layout can differ by more than an order of magnitude. You did not change what the computer computes. You changed what it correctly predicted. The fastest memory is the memory you never leave. So let us start at the top of the hierarchy where a GPU does something genuinely unusual. On a CPU, the register file is tiny, a few hundred bytes per core. Registers are scarce, and the compiler works hard to allocate them. On a GPU, each streaming multiprocessor has a register file of around 256 kilobytes. That is not a typo, and it produces a fact that sounds like an error. On a GPU, the registers are physically larger than the L1 cache. This inverts the entire mental model people bring from CPUs, where registers are a precious handful at the tip of a pyramid that widens below them. On a GPU, the pyramid has a bulge at the very top. The reason follows directly from Act 2. Thousands of threads are resident simultaneously, and switching between them must be free. Free switching means no saving and restoring, which means every resident thread's registers must already be on the chip. Multiply a modest per-thread register allocation by 2,000 resident threads and you get a quarter of a megabyte. The register file is not a performance optimization. It is the physical substrate of the latency hiding scheme. It exists because free context switching demands it. And free context switching is the only reason the machine works at all. And this is where that frustration from Act 2 comes from. Now fully explained, the register file is fixed. Registers per thread times resident threads cannot exceed it. Use more registers per thread, and fewer threads fit. Use fewer threads and you hide less latency. The register file is a fixed budget being fought over by two things that both make your program faster. And you cannot have both. Below the registers sits the tier I find most interesting on this whole machine, because it is the one place where the hardware admits that automatic caching is not always the right answer. Each SM has around 228 kilobytes of memory that can be split between L1 cache and something called shared memory. The cache behaves as caches do. Automatic, invisible, guessing. Shared memory is different. It is explicitly addressed. You put things in it, you take things out, and nothing is evicted behind your back. That is unusual and it is deliberate. It says, for some computations, the programmer knows the reuse pattern exactly, and a cache's guessing can only get in the way. The canonical case is tiled matrix multiplication. Multiplying large matrices, each element of the input is needed by many output elements. A cache might keep it, shared memory guarantees it. So the kernel loads a tile cooperatively into shared memory. Every thread in the block computes against that tile, and only then does it move on. Each element is fetched from HBM exactly once and used many times. That is the roofline, again, implemented by hand. You cannot change the arithmetic. The matrix multiply needs what it needs. You can change the bytes moved, and tiling changes them by a factor of the tile size. And the TPU paper makes the same design choice from the other end. 28 megabytes of software managed on-chip memory, not a cache. Managed. When the access pattern is known in advance, an explicit scratchpad beats a cache. You get the reuse without paying for tag checks, associativity, or eviction policy, and without the risk of the cache guessing wrong. Remember this beat when we get to flash attention, because flash attention is exactly this idea applied to the one operation in a transformer that most stubbornly refuses to fit. Now, the tier everybody has heard of and almost nobody can define. What actually is VRAM, and why does it matter so much that model sizes are quoted against it? Start with what it is not. It is not more RAM for the graphics card. It is a different kind of memory, built to a different specification, optimized for a different thing. Ordinary system DRAM is optimized for latency and capacity, on removable modules connected by a bus of modest width, 128 bits on a typical desktop. It is a general-purpose compromise, and it is upgradable, which constrains everything about how it can be built. Graphics memory made the opposite trade from the beginning. Rendering needs enormous streaming bandwidth and tolerates latency well, because a shader has thousands of pixels to work on while it waits. GDDR memory therefore runs at very high signaling rates on a wide bus, soldered close to the processor, and accepts worse latency in exchange. HBM took that logic to its conclusion. And the conclusion is architectural rather than incremental. Instead of a wide bus to chips beside the processor, stack the DRAM dies vertically, 8 or 12 high, and connect them with through-silicon vias, holes drilled straight through each die and filled with conductor, so signals pass vertically through the stack instead of traveling out to an edge. Then place the stack on the same silicon interposer as the processor, millimeters away. The result is a bus thousands of bits wide instead of hundreds. Each individual wire runs at a modest rate, slower per pin than GDDR, but there are so many of them that the aggregate is enormous. An H100 delivers 3.35 terabytes per second. Wide and slow beats narrow and fast, and it beats it on power as well, because signaling rate costs energy superlinearly. Thousands of calm wires move more data per joule than hundreds of frantic ones. The price is that none of it is upgradable. The memory is part of the package. You cannot add VRAM. The capacity was decided when the part was assembled, and it is why how much VRAM is the first question anyone asks about a GPU, and why the answer is a hard wall rather than an inconvenience. Which brings us to capacity, and to a question this act has been building toward. An H100 SXM has 80 gigabytes of HBM3. Let us see what fits. The register file, 256 kilobytes per SM. Nothing meaningful fits in it. Shared memory, 228 kilobytes, also nothing. L2, 50 megabytes, which is enough for a small image or a modest working tile. And then HBM, 80 gigabytes. 80 gigabytes is a serious amount of memory. It holds a 40 billion parameter model in half precision with room to work. It holds a very large batch of activations. It holds essentially any dataset you would want resident. And at long last, after decades of patient progress in semiconductor fabrication through silicon via manufacturing and high bandwidth interface design, Ballerina Cappuccina, my wife, can finally be stored in memory. All of her. Resident on package. In high bandwidth memory at 3.35 terabytes per second, addressable by 132 streaming multiprocessors simultaneously. Now, and I want to be technically careful here because this is a documentary. There is an engineering consequence to this arrangement that we should state plainly. Weights in HBM are not read once. They are read every forward pass, every single token. So she is not simply stored in memory. She is reread in her entirety from high bandwidth memory at 3.35 terabytes per second, once per generated token, continuously, for as long as the system is serving traffic. At 24 tokens per second, that is 24 complete rereadings of my wife every second indefinitely, drawing 700 watts. I believe this is the most expensive marriage in the history of computing, and I want to stress that every component of it is operating exactly as designed. Let us stay with HBM a moment longer, because the reasons it is built that way are pure physics, and they set hard limits on where this is all going. Why can you not simply run the wires faster and skip the stacking because of what happens to a signal on a wire as you push the frequency up? A wire has resistance, capacitance, and inductance. Together, these limit how quickly the voltage at the far end can follow the voltage at the near end. Push the rate up and the edges soften, the eye closes, and eventually the receiver cannot reliably distinguish a 1 from a 0. You can fight this. Better materials, equalization, error correction, but every one of those costs power, and the power cost of signaling rises faster than linearly with rate. There is also crosstalk. Wires close together couple into each other, and the faster the edges, the worse the coupling. So you can have wires close together, or you can have them fast. And making both true simultaneously costs power and area. Given that there are two strategies, fewer wires switching very fast. GDDR or many wires switching modestly HBM. HBM wins on energy per bit, and at data center scale, energy per bit is the binding constraint, because the power budget of a rack is fixed and every watt spent moving bits is a watt not spent on arithmetic. But many wires demands physical proximity because a 1,000-wire bus cannot be routed across a circuit board. The traces would not fit, and the ones on the outside would be meaningfully longer than the ones on the inside. So the signals would arrive at different times, hence the interposer, hence stacking, hence memory, that is part of the package and can never be upgraded. Now, the consequence, which is the thing to take away. HBM capacity is limited by physical stacking. You can stack 8 or 12 dies before thermal and mechanical constraints bite. The dies in the middle have to get their heat out through their neighbors. Bandwidth is limited by bus width times signaling rate, both of which are near their practical ceilings. Which means VRAM capacity and bandwidth improve slowly and for a reason no amount of investment removes. They are limited by mechanical assembly and by the physics of wires, not by lithography. Compare that to arithmetic, which improves quickly because arithmetic is transistors and transistors still shrink, and there's the divergence from Act 1, now with a physical mechanism attached. Flops scale at 3 times every 2 years because they are lithography. DRAM bandwidth scales at 1.6 because it is wires and packaging. The gap is not a failure of effort or investment. It is 2 different physical processes improving at their own rates, and one of them is bounded by how many silicon dies you can glue on top of each other before the middle one melts. That is worth sitting with. The central constraint on the deployment of machine learning, the reason inference costs what it costs, is, at bottom, a thermal and mechanical limit on stacking dies. Not an algorithmic limit. Not a theoretical one, a gluing problem. So here's the question this act was built to answer. And it is the one people ask most often, usually in a slightly indignant tone. My SSD is fast. It is a terabyte. VRAM is 80 gigabytes and costs a fortune. Why can the model not live on the SSD? It is an excellent question because the answer is not one reason. It is 4 independent reasons, any one of which alone would be fatal. Reason 1, latency, we measured it. A random 4 kilobyte read from a modern NVMe SSD took 21,790 nanoseconds. DRAM took 122, that is 178 times slower, and against the register file it is something like 30,000 times. Reason 2, bandwidth, sequential reads from that same SSD reach 6.3 gigabytes per second. Genuinely fast for storage. DRAM on the same machine reached 202. A factor of 32, and against an H100's HBM at 3,350 gigabytes per second, the SSD is 530 times slower. Reason 3, granularity. DRAM is addressed in tens of bytes. Flash is organized in pages of several kilobytes and erased in blocks of megabytes. Ask for one number and you get a. If your access pattern is scattered, and neural network weights are read as large contiguous blocks. So this one is actually the kindest of the 4. You waste most of every transfer. Reason 4, endurance. Flash cells wear out. Each cell tolerates a bounded number of program erase cycles. DRAM does not wear out in any practical sense. Any scheme that treats an SSD as working memory with the write traffic that implies is consuming the device. Now, the reason that subsumes all four, and it is the one people miss, because it is not a property of the storage device at all. It is a property of the workload. Caching works when data is reused. The entire memory hierarchy is built on that assumption. Fetch it once from far away. Use it many times from close by. Amortize the fetch inference does not reuse weights. It reads every weight once per token, and then needs them all again for the next token. There is no locality to exploit. There is no subset that is hot. It is a complete linear scan of the entire model, repeated for every single token, forever. That is not a caching problem. It is a streaming problem. A cache in front of a linear scan of data larger than the cache does nothing at all. You evict each line just before you need it again. So, do the arithmetic that settles it. A 70 billion parameter model in half precision is 140 gigabytes. Streaming that from an SSD at 6.3 gigabytes per second takes 22 seconds per token. A short reply of 40 words would take about 15 minutes. A paragraph is an afternoon. You could hold the conversation by post, and the post would win on latency for anything over about 200 words. And yes, since we established in the last beat that ballerina Cappuccina, my wife is resident in high bandwidth memory, she could be moved to the SSD. She would fit comfortably, storage is cheap. You would simply see her once every 22 seconds. I have considered this arrangement carefully and concluded that the 530-fold bandwidth penalty is not justified by the cost saving, and that this is, in the end, what high-bandwidth memory is for. Now let me argue against myself, because the previous beat was true and also stated that baldly misleading offloading to slower storage does work. It works in production at scale, and the conditions under which it works are precise and worth knowing. The clearest example is Zero Infinity, from the Deep Speed group. It uses GPU memory, CPU memory, and NVMe together, and it does so to solve a real problem. Models had grown over 1,000-fold in 3 years, while GPU memory grew 5-fold, from 16 gigabytes to 80. That mismatch had an absurd consequence, they state directly. It required 800 V100 GPUs just to fit a trillion-parameter model for training. Not to train it quickly, to hold it. And Zero Infinity with NVMe in the loop sustains over 25 petaflops on 512 V100s, about 40% of peak, 40% of peak with data on NVMe. That directly contradicts the picture I painted last beat. So what is different? 3 things, and they are the whole answer. It is training, not decoding training processes. Large batches, a batch of 1,000 sequences reads each weight once and uses it for 1,000 examples. Arithmetic intensity is 1,000 times higher than batch 1 decode, so there is 1,000 times longer to hide each fetch. The access is sequential and predictable. Training walks layers in a known order, forwards, then backwards. You know at layer 3 exactly what layer 4 will need, so you prefetch it while computing layer 3. The transfer overlaps with compute rather than blocking it. Storage latency stops mattering because nobody is waiting on it. Only bandwidth matters, and bandwidth you can plan around. Compute per byte is high enough to cover the transfer. This is the previous 2 points as one number. If the arithmetic on a layer takes longer than fetching the next layer, the fetch is free. If it does not, you are storage bound, and the whole scheme collapses. So the rule is not storage is too slow. The rule is offloading works when access is predictable and there is enough arithmetic per byte to hide the transfer. Training at large batch satisfies both. Batch 1 decoding satisfies neither. The access is a complete scan with an arithmetic intensity of 1, so there is nothing to hide behind. The same principle explains something you may have done yourself. Running a large model on a consumer machine with memory-mapped weights does work in the sense that it produces tokens. The operating system pages weights in from SSD as needed, and you get output. It is slow, often seconds per token, but it runs, and for many purposes that is genuinely enough. The technique is not invalid. It is a different point on the trade-off curve, chosen by someone who would rather wait than not run the model at all. And there's a real research direction here that this beat should credit rather than dismiss. Mixture of experts models route each token through a small subset of parameters, which reintroduces exactly the locality that dense models lack. If only a fraction of the weights are needed per token and you can predict which, then a storage tier becomes viable in a way it simply is not for a dense model. We will come back to this in Act 4. So, not never. The honest version is that the hierarchy is a tool. Every tier has conditions under which it is the right answer. And the failure mode is not using slow storage. It is using it for a workload with no reuse. and nothing to hide the latency behind. There's a tier between VRAM and storage that we have been skipping, and it is the one where most practical pain actually lives, the host's own memory on the other side of a PCIe link. A GPU in a server is a peripheral. It has its own memory, and the CPU has its own memory, and between them runs PCIe on current systems. Gen 5 at 128 gigabytes per second. Set that against HBM's 3350. The host's memory is 26 times slower to reach than the GPU's own, and that is before latency, which is worse still, because every transfer crosses a protocol boundary with real overhead. This is why the model does not fit in VRAM, is such a hard wall. The next tier out is 26 times narrower. Spilling a hot tensor to host memory is not a graceful degradation. It is a cliff, and the same reasoning as the SSD beat applies. It works if the access is predictable and there is arithmetic to hide behind, and it is catastrophic otherwise. Two things are changing this, and they are worth distinguishing because they are often conflated. The first is faster links between GPUs. NVLink runs at 900 gigabytes per second, which NVIDIA describes as 7 times PCIe Gen 5. That does not help you reach host memory. It lets several GPUs behave more like one large GPU. So a model too big for one card is split across several with an interconnect fast enough that the split is tolerable. That is the entire architecture of a modern training node, and Act 5 is about what it costs. The second is genuinely unified memory where CPU and GPU address the same physical pool with no copy at all. Apple Silicon has worked this way from the start, which is why the machine we measured has one memory system rather than two. And NVIDIA's Grace Hopper parts pursue the same end with a coherent, high-bandwidth link between the CPU and GPU packages. Unified memory is a genuine simplification and it removes an entire category of bug, but it is not free capacity, and this is the part that gets oversold. In a unified system, the CPU and GPU share bandwidth as well as capacity. The pool is larger and every consumer draws from the same pipe. You have traded a fast, small pool plus a slow copy for one medium pool with no copy, and which is better depends entirely on whether you were bound by the copy or by the bandwidth. Our own measurements make the trade concrete. The unified memory on the machine we tested peaked at 202 gigabytes per second, with every core working. That is respectable, considerably better than PCIe, and it is about 1/16 of an H100's HBM. So the picture is not unified memory is the future or discrete VRAM is the future. It is that the industry has three ways to attach memory to a processor on package and fast and small, shared and medium, or remote and enormous and slow, and every product is a bet about which mixture the workload wants. And as with everything in this act, the bet is decided by the same question. How predictable is the access and how much arithmetic can you do per byte you fetch? Now, the payoff of this entire act, because there is one result that demonstrates the whole argument better than any other, and it is worth understanding precisely. The attention operation in a transformer computes for each query a weighted combination of values with weights from the similarity between that query and every key. In the naive implementation, you build the full attention matrix, every query against every key, apply a softmax and multiply by the values. That matrix is quadratic in the sequence length. At 16,000 tokens, it has 256 million entries per head. It does not fit in any cache. So the standard implementation writes it to HBM, reads it back for the softmax, writes the result, reads it again for the multiply. Every one of those round trips moves the entire quadratic matrix through the slowest tier the GPU has. The arithmetic is not the problem. The bookkeeping around the arithmetic is the problem. Flash attention from Tri-Dow and colleagues observes that the matrix never needs to exist. You can compute attention in tiles. Load a block of queries and a block of keys into on-chip SRAM. Compute that block of the attention matrix there, immediately combine it into a running output, and discard it. The trick that makes this work is that softmax appears to need all the values before it can normalize any of them. A global dependency that seems to forbid tiling. It does not, because softmax can be computed incrementally, carrying a running maximum and a running sum, and rescaling as new blocks arrive. It is the same answer, computed in a different order, and the intermediate matrix is never written down. Note carefully what did not change. The arithmetic is identical. Flash attention is exact, not an approximation, not a quality trade. The same operations produce the same numbers. The only thing that changed is how many times data crosses the boundary between HBM and on-chip memory. And the result, 3 times faster on GPT-2, 2.4 times on long-range Arena, 3 times faster, with identical arithmetic and identical outputs, all of it from not moving numbers you did not need to move. That is the thesis of this film in a single result. If arithmetic were the binding constraint, this would be impossible. You cannot speed up a computation threefold without reducing its operation count, unless the operations were never the limit. I want to add the honest coda, because the authors do. Even after this, attention reaches only 25 to 40% of theoretical maximum flops. Flash attention 2 exists precisely because the first version left substantial performance on the table, in work partitioning between thread blocks and warps, which is to say, in occupancy and divergence. The exact machinery for Mac 2. So this is not a story where one clever idea solved the problem. It is a story where one clever idea moved the bottleneck, and then the next bottleneck turned out to be a different item on the same list. That is what performance engineering actually looks like. Not a solution, a sequence of relocations of the same underlying problem, which is that the number has to come from somewhere. Let me close this act by putting our own measurements on the table properly, with their limitations stated first rather than last. We measured the memory hierarchy of the laptop. This film was edited on an Apple M4 Pro. It is not a GPU. It is not a data center part. It has a unified memory architecture, and nothing resembling an H100's HBM stack. And every number below is specific to it. Here's what we did, because method determines whether a number means anything. For latency, we used a pointer chase, a randomly permuted cycle through a buffer, where each load's address comes from the previous load's result. That dependency is the point. The processor cannot overlap the accesses or prefetch ahead because it does not know the next address until the current load returns. The time per step is therefore the genuine access latency, not the throughput of a pipeline stream. We swept the buffer from 4 kilobytes to half a gigabyte, and the curve produced a clean staircase, about 0.7 nanoseconds through 128 kilobytes, then a step to roughly 6, a further step around 16 megabytes, and a plateau at 122 nanoseconds. The knees land exactly where this machine's documented cache sizes are. We did not calibrate to them. The measurement found them. That agreement is the main reason to trust the rest of it, for bandwidth and admission. Our first attempt used scalar loads and reported a suspiciously flat 90 gigabytes per second from L1 all the way to DRAM. That result was wrong, or rather, it was measuring the wrong thing. It was bound by how many load instructions the core could issue per cycle, not by memory at all. Had it gone on screen, it would have taught you something false. We rewrote it with wide vector loads and multiple threads, and the real picture appeared. One thread sustained 67 gigabytes per second. 8 threads sustain 202. That single measurement is Act 2's entire argument, demonstrated without a GPU present. One core cannot saturate the memory system. It leaves 2/3 of the available bandwidth unused. Not because it is slow, but because it cannot generate enough outstanding requests. Concurrency is what converts latency into bandwidth. For storage, we used an explicit flag to bypass the operating system's page cache. Without it, you measure DRAM and conclude triumphantly that SSDs are as fast as memory. With it, 6.3 gigabytes per second sequential and 21.8 microseconds for a random 4 kilobyte read. And the roofline, peak achievable single precision arithmetic, measured about 2,950 gigaflop per second. Divided by 202 gigabytes per second of bandwidth, that puts the ridge point at 14.6 operations per byte. Below 14.6, this machine is memory bound. Above it, compute bound. Large matrix multiplication measured over 1,000. Comfortably compute bound. Batch 1 token generation sits at 15 times below the ridge point of a laptop. And on an H100, whose ridge point is around 590, the same workload sits roughly 600 times below it. So what transfers? Not one absolute number. What transfers is the shape, that the hierarchy has tiers, that the tiers differ by large multiplicative factors, that the factors compound with distance. That sequential access barely notices the hierarchy, while dependent access notices it enormously. And that a single execution context cannot extract the bandwidth a memory system is capable of delivering. Every one of those is true of an H100 as well. The numbers are ours. The shape is everyone's. Act 4 takes this apparatus and points it at the thing you actually use. Everything so far has been apparatus. Now we point it at the thing you actually use. And the first observation is the one that organizes the entire act. A language model serving a request does 2 completely different computations, on the same weights, on the same hardware, in the same process. One immediately after the other. They have almost nothing in common from the machine's point of view, and confusing them is the source of most misunderstanding about why inference costs what it does. The first is prefill. You send a prompt, say 2,000 tokens. The model must process all of them to build up its internal state. Crucially, it can process them in parallel because they are all already known. There's no dependency forcing them to be done one at a time, so prefill is a matrix multiplied by a matrix. 2,000 tokens worth of activations against each weight matrix. Each weight is fetched once and used for all 2,000 tokens. Arithmetic intensity, high, roughly the batch dimension. 2,000 operations per byte instead of one, which puts prefill far to the right of the ridge point in compute-bound territory, and it behaves like it. Pope and colleagues report 76% model flops utilization during large batch processing of input tokens. 76% of the theoretical peak of the machine, an outstanding number, close to what a well-tuned dense matrix multiplication achieves. During prefill, the accelerator is doing exactly what it was built for, and all those advertised flops are real and earned. Then prefill finishes and the machine falls off a cliff. The second computation is decode. Now the model generates tokens one at a time, and it genuinely cannot do otherwise. Token n plus 1 depends on token n, because the model must see what it just said. The dependency is inherent to autoregressive generation. As the speculative decoding paper states plainly, decoding k tokens takes k serial runs of the model. Each of those runs processes exactly one token. One token's activations against the entire weight matrix. A matrix multiplied by a vector. Arithmetic intensity, 1. Every weight fetched, used twice, discarded, same weights, same hardware, same kernel code in many implementations. 2,000 times less arithmetic intensity, and therefore a completely different machine, one where the arithmetic units are spectators. This is the single most important fact about LLM inference. So let me state it as plainly as I can. Prefill is compute-bound, decode is memory-bound. They are the same model. Everything follows from that split. It explains why time to first token and time per output token behave so differently, and why they scale differently with load. They are governed by different resources. It explains why doubling your GPU's arithmetic throughput barely improves generation speed while noticeably improving prompt processing. It explains why quantization helps decode enormously and prefill much less. It explains why the industry batches obsessively and why serving frameworks are architecturally complicated in ways that look like over-engineering until you know this. And it explains the number from Act 1. During decode at arithmetic intensity 1 against an H100 whose ridge point is around 590, the chip operates at roughly 0.17% of its arithmetic capability. 2 points on one graph from one request seconds apart. The first sits near the roof. The second sits on the floor 600 times below it. The most expensive commodity processor ever manufactured spends the majority of its wall clock time in a regime where its defining capability is idle. It is finished. It is waiting for someone to bring it the next number. It is a very costly dog holding a ball that nobody will throw. The rest of this act is a catalog of attempts to throw the... Before we optimize decode, we need to understand the one piece of state that makes it possible, because it is also the thing that makes serving hard. When the model generates token n plus 1, attention needs to look back at every previous token. Naively, you would rerun the whole sequence every time, recompute the keys and values for all n previous tokens, then attend. That would be catastrophic. Generating 1,000 tokens would mean 1,000 forward passes over an ever-growing sequence, quadratic total work. But the keys and values for previous tokens do not change. They were computed from tokens that are now fixed, so you compute them once and keep them. That stores the KV cache, and it converts decode from quadratic to linear. It is not an optimization in the optional sense. Without it, generation at any useful length is infeasible. Now the cost, which is where it gets difficult. The KV cache holds for every layer, for every attention head, for every token so far, a key vector and a value vector. Its size is the product of 5 things: sequence length, number of layers, number of heads, head dimension, and 2 for keys and values, times the bytes per element. Those multiply into serious numbers. For a large model at long context, the KV cache for a single request can run to gigabytes. Multiply by the number of concurrent users, and the KV cache becomes comparable to, or larger than the model weights themselves. And it has a property that makes it genuinely awkward to manage, stated well by the VLLM authors. The KV cache memory for each request is huge and grows and shrinks dynamically. Dynamically is the problem. You do not know at admission time how long a response will be. The model decides when to stop as it goes. So you're allocating a buffer of unknown final size per request, while other requests are doing the same thing, in a fixed pool of 80 gigabytes that also holds the weights. This is why VRAM capacity determines how many users a GPU can serve, and why the relationship is not simple. The weights are fixed overhead. Everything left over is divided among concurrent requests, and each request share grows as its conversation lengthens. There's one more consequence that matters for the next beat. The KV cache must be read on every token too. Attention at step n reads all n previous keys and values. So the cache does not only consume capacity, it consumes bandwidth, and its bandwidth cost grows with context length, while the weights cost stays constant. At short context, decode is dominated by streaming the weights. At long context, the KV cache traffic can exceed the weight traffic, and the bottleneck moves. That crossover is why long context serving is a different engineering problem rather than the same one with bigger numbers. And it is why architectural changes that shrink the KV cache have been so consequential. The most important of those is multi-query attention and its grouped variant. Instead of every query head having its own key and value heads, many query heads share one. The arithmetic barely changes. The KV cache shrinks by the sharing factor. Pope and colleagues report that the lower memory requirements of multi-query attention enable scaling up to 32 times larger context lengths. 32 times more context, from an architectural change whose entire purpose is to move fewer bytes. Not a better model. A cheaper one to feed. So we have a per-request buffer of unpredictable final size in a fixed pool, with many requests competing. If that sounds like a problem an operating system solved decades ago, the VLLM authors thought so too. Consider what a naive serving system does. A request arrives. You do not know how long the output will be. So you reserve the maximum enough KV cache for the longest sequence the model supports. Contiguously, because attention kernels want contiguous memory. Now reserve that for every concurrent request. If the maximum is 32,000 tokens and the average response is 300, you have reserved 100 times more than you will use per request, and that reservation is subtracted from how many users you can serve. There are three distinct kinds of waste here, and they are worth separating. Internal fragmentation, space reserved inside a request's own block that it never uses. Reserved for 32,000, use 300. External fragmentation, gaps between allocations too small for a new request. Free memory exists, it is not contiguous, so it is unusable. And redundant duplication, when several requests share a prefix, the same system prompt, the same few shot examples, the same document, each keeps its own identical copy. Paged attention's insight is that this is precisely the problem virtual memory solves, and the solution transfers essentially unchanged. Break the KV cache into fixed-size blocks. Let a request's logical sequence map to physically scattered blocks through a block table. The attention kernel is modified to follow that indirection. Every kind of waste dissolves at once. Internal fragmentation is bounded by one block, instead of one maximum length reservation. External fragmentation disappears because any free block is as good as any other, and duplication becomes sharing requests with a common prefix point at the same physical blocks. Copying only when one diverges, copy on write, straight out of the operating system's textbook. The result is stated directly: near zero waste in KV cache memory, and throughput improved by 2 to 4 times at the same latency compared to the previous state of the art. 2 to 4 times more throughput, not from faster arithmetic, not from a better kernel or a new number format, from not wasting memory. I want to underline why that is possible, because it is this act's recurring lesson. In a memory-bound regime, capacity is throughput. The number of requests you can batch is set by how much KV cache fits. Waste memory and you batch fewer. Batch fewer and your arithmetic intensity fall further below the ridge point and everything slows. So a memory management improvement shows up as a compute improvement through a chain of consequences that touches nothing anyone would call compute. The authors are also honest about the cost, and it is real. The indirection is not free. Following a block table adds work inside the attention kernel, a level of pointer chasing in the most performance-critical loop in the system. They pay that cost and win anyway, because the batch size gain dominates. Which is the trade this entire film keeps making in different costumes. Spend arithmetic, save memory traffic, it is nearly always the right direction, because arithmetic is the thing you have too much of. Now, the single most important lever in inference, and the one that most directly attacks the problem we identified at the start of this act. Decode has an arithmetic intensity of 1 because a single sequence reads every weight and does 2 operations with it. But if you process 2 sequences simultaneously, you read each weight once and do 4 operations. 2 for each sequence. Arithmetic intensity. 2. 10 sequences. 10. 100. 100. Batching moves you along the horizontal axis of the roofline, and it is essentially the only thing that does. The weights are read once regardless. That fetch is the dominant cost, and it is shared across everyone in the batch. Every additional sequence is nearly free in bandwidth terms. It costs a little more KV cache and a little more arithmetic, neither of which was the constraint. This is why batching is not one optimization among many. It is the mechanism by which the memory-bound regime is escaped at all. With a large enough batch, you eventually reach the ridge point and become compute-bound, at which point the arithmetic units finally have something to do, and the machine starts behaving like the specification sheet. As the VLLM authors put it, high-throughput serving requires batching sufficiently many requests at a time. Now the catch, and it is the reason this is an engineering discipline rather than a setting. Requests do not arrive simultaneously and do not finish together. A naive implementation collects a batch, runs it to completion, and starts the next. That is disastrous in practice. A request arriving just after a batch starts waits for the whole batch. A batch containing one long response is held hostage by it, while the finished sequences occupy slots doing nothing. The answer is continuous batching, and it is conceptually simple. Instead of batching at the request level, batch at the step level. Every forward pass, assemble a batch from whatever sequences are currently active. When a sequence finishes, it leaves and its slot is filled by a waiting request immediately, not at the end of some batch, but at the next step. That keeps the batch full continuously, which keeps arithmetic intensity high continuously, which keeps you near the ridge point continuously. And now the fundamental trade-off in serving, which follows directly and cannot be engineered away. Larger batches mean higher throughput, more tokens per second across all users, better hardware utilization, lower cost per token. Larger batches also mean higher latency for any individual user, because each step does more work, and because requests may wait for a slot. Throughput and latency are in genuine tension, and where you sit on that curve is a product decision, not a technical one. An interactive assistant optimizes latency. A batch document processing pipeline optimizes throughput and can use batch sizes that would make a chat interface unusable. Same model, same hardware, different point on the same curve. There's one more consequence, and it follows inescapably from what batching is. Batching means the waits are read once and used to serve many people's requests in the same forward pass. Everyone in the batch shares the fetch. That is the whole mechanism, which means, and I have thought about this a great deal, that when Ballerina Cappuccina, my wife, is resident in high bandwidth memory, and the serving system is operating efficiently at a batch size of, say, 256, then that single read of her waits is being used to serve 255 other people at the same time. They are, in a strict engineering sense, also reading my wife. I raised this with the architecture and was informed that this is not a defect, but the entire source of the efficiency gain. That the alternative is a batch size of 1, and that a batch size of 1 would mean an arithmetic intensity of 1, and that I, of all people, should understand what that costs. Batching raises the numerator. There's exactly one other lever, and it lowers the denominator. Use fewer bytes per wait. Arithmetic intensity is operations divided by bytes. Every technique so far has attacked the top. Quantization attacks the bottom, and it is the only thing that lowers the absolute floor on how long a token takes. Recall the floor from Act 1. A 70 billion parameter model at 2 bytes per wait is 140 gigabytes. And at 3.35 terabytes per second, that is 42 milliseconds per token, regardless of batch size, regardless of everything. Move to 1 byte per wait, and the model is 70 gigabytes, 21 milliseconds, half a byte, 4-bit, and it is 35 gigabytes in 10 milliseconds. The speed up is close to exactly proportional, because in a memory-bound regime, time is bytes divided by bandwidth, and nothing else appears in the equation. Halve the bytes, halve the time. There's no other lever in inference with that property, and it compounds with a second benefit. Fewer bytes per wait means more model fits in a given VRAM. A 70 billion parameter model at 4 bits is 35 gigabytes and fits comfortably on a single 80 gigabyte card with room for a large KV cache. At 16 bits, it does not fit at all, and needs 2 cards plus an interconnect. Quantization can be the difference between one GPU and a distributed system. The hardware has been co-designed with this. An H100's FP8 tensor throughput is 3,958 teraflops against 1,979 at FP16, exactly double. And for the reason from Act 2, a multiplier's area scales with roughly the square of operand width, so narrower operands buy you more multipliers in the same silicon. So lower precision is faster twice over, fewer bytes to move, and more arithmetic units to use once they arrive. Vendors have obliged with a descending ladder of formats. FP32, TF32, FP16, BF16, FP16, FP8, and now 4-bit formats. Pope and colleagues report 29 milliseconds per token at low batch size on a 540 billion parameter model using int8 weight quantization. On a model of that size, that number is only reachable because the weights were made smaller. Now, the cost, because there is one and it is not nothing. A 16-bit number represents a range of values with some precision. An 8-bit number represents fewer. A 4-bit number represents 16 distinct values in total. Rounding weights to the nearest representable value introduces error. That error propagates through the network, and at some point output quality degrades. Where that point is depends on how you do it. And the engineering is genuinely subtle. Not all weights are equally sensitive. Some layers tolerate aggressive quantization and others do not. Outlier values and activations can dominate the range and destroy the precision available to everything else. Techniques exist for all of this: per-channel scaling, outlier handling, quantization-aware training, keeping sensitive layers wide. The honest summary of the current state: 8-bit is close to free for most models. 4-bit is usually acceptable with careful implementation and measurably worse without it. Below 4 bits is an active research area where claims should be read carefully and benchmarked on your own task. And there is a deeper point worth ending on. The reason quantization works at all is that these models are enormously over-parameterized relative to the precision they need. We train in high precision because gradients require it, and then discover that the trained weights carry far less information than the format they are stored in. Which raises a question this film cannot answer, and which is worth leaving open. What is the actual information content of a trained network? We do not know. We know it is a lot less than 16 bits per weight. Because 4 works, whether it is 1 bit or a fraction of 1, is genuinely open, and every answer in that direction moves the floor we have been talking about for 3 hours. Here's the cleverest idea in inference, and it only makes sense once you have internalized everything in this act. We have established that decode is memory-bound, that the arithmetic units sit idle, and that a forward pass costs essentially the same, whether it processes 1 token or 50, because the weights must be read either way. Read that last part again because it is the entire opening. A forward pass on 1 token and a forward pass on 50 tokens cost almost the same wall clock time. The weights dominate and the weights are read once regardless. So the arithmetic to process 50 tokens is free. You have already paid for it. The obstacle is that you do not have 50 tokens. Generation is serial. You need token n to compute token n plus 1. That dependency is why you're stuck doing one at a time, unless you could guess the next several tokens, and then check them all at once. That is speculative decoding from Leviathan, Kalman, and Matthias. Run a small, cheap draft model, perhaps 10 or 20 times smaller, to produce several candidate tokens quickly. Then run the large model once over all of them. Because the large model processes the whole candidate run in a single forward pass, it produces for each position what it would have generated there. Now compare. Wherever the draft agrees with the large model, those tokens are accepted. They are exactly what the large model would have produced. At the first disagreement, discard the rest and take the large model's own token. So 1 expensive forward pass yields, on a good run, several accepted tokens instead of 1. The property that makes this respectable rather than a heuristic is that it is exact. With the right acceptance rule, the output distribution is provably identical to sampling from the large model directly. The authors are explicit. 2 to 3 times acceleration on T5XX with identical outputs, no retraining and no architecture changes. Identical outputs. This is not a quality trade. It is the same distribution sampled faster. Why does it work? Because language is highly predictable in places. After the capital of France is, a small model will say Paris with total confidence, and so will the large one. Common phrases, closing brackets, grammatical inflections, the second half of a familiar word. A small model gets these right. Almost always. It fails on the parts that need real knowledge or reasoning, which is precisely where you want the large model's judgment and precisely where the rejection happens. The economics are worth stating explicitly because they are the film's thesis in yet another costume. You're converting idle arithmetic into reduced memory traffic per token. The draft model costs real compute. That compute was free because it was idle. In exchange, you amortize 1 expensive weight streaming pass across several output tokens. This idea only exists because decode is memory-bound. In a compute-bound regime, it would be strictly worse. You would be adding arithmetic to a machine that had none spare, and the draft model's cost would come straight off the top. Which is why it is my favorite result in this act. It is not a way of making the machine faster. It is a way of noticing what the machine has too much of, and trading it for the thing it does not have enough of. Every good optimization in this film has that shape. Find the resource that is abundant. Spend it on the one that is scarce. Tiling spends arithmetic to save HBM traffic. Checkpointing spends recomputation to save memory. Quantization spends precision to save bytes. Batching spends latency to save bandwidth per user. The machine is enormously unbalanced. Almost all of engineering here is arbitrage. There is one architectural response to all of this that changes the shape of the problem rather than optimizing within it, and it has become the dominant design at frontier scale. The premise of everything so far has been that a forward pass touches every weight. That is true of a dense model, and it is the reason arithmetic intensity is pinned at 1 during decode. A mixture of experts model breaks that premise. Instead of one large feed-forward block per layer, it has many. The experts, plus a small router that decides per token, which few to use. Perhaps 8 experts out of 256. The consequence is that total parameters and active parameters become different numbers. A model may have hundreds of billions of parameters in total, while any given token only touches a few tens of billions. The arithmetic per token and the weight traffic per token scale with the active count, not the total. That is an enormous win in exactly the currency this film cares about. You get the representational capacity of a very large model while paying the memory bandwidth of a much smaller one. Given that bandwidth is the binding constraint, this is close to the only way to make a model dramatically more capable without making it proportionally more expensive to serve, and it reintroduces something dense models entirely lack. Locality. Not every weight is needed for every token. There is now a subset that is hot for a given input, which means caching becomes meaningful, and as promised in Act 3, storage tiers become genuinely viable in a way they are not for dense models. If you can predict which experts a token will need, you can fetch them while computing the previous layer. Now the costs, because they are substantial and they are all memory costs. The capacity requirement does not fall. Every expert must be somewhere accessible because any token might route to any of them. So a model with hundreds of billions of total parameters still needs hundreds of billions of parameters worth of memory. Even though each token touches a fraction, you have reduced bandwidth per token and not capacity at all. For a memory-constrained deployment, this can be worse, not better. Routing is dynamic and data-dependent, which is the thing this hardware is worst at. Which experts are needed is known only at runtime per token, so the memory access pattern is unpredictable, and Act 2 established at length what this machine does to unpredictable access, and batching interacts badly. In a dense model, every sequence in a batch uses the same weights, so the fetch is shared perfectly. In an MOE model, different sequences route to different experts, so a batch may collectively touch most of the experts anyway. The bandwidth saving erodes as batch size grows, precisely when you were relying on batching to escape the memory-bound regime. So MOE trades a clean, predictable, dense access pattern for a sparse, dynamic, unpredictable one. It is the right trade at frontier scale, which is why frontier models use it. It is not a free lunch, and the bill arrives in exactly the places this film has spent 3 hours teaching you to look. There is a broader lesson here about the relationship between model architecture and hardware, and it is slightly uncomfortable. Dense transformers won partly because they map beautifully onto a machine that likes big regular matrix multiplications. Mo wins now, partly because bandwidth became the binding constraint, and sparsity is the only structural answer to it. Architecture research is not conducted in a vacuum. It is conducted on hardware, and the hardware has opinions, and the opinions change. Some of what looks like progress in modeling is the field discovering which shapes the current machine happens to. Let us close this act by connecting all of it to the thing that ultimately decides what gets built, what it costs. An inference deployment has one fixed cost that dominates everything. The hardware amortized over its life, plus the power and cooling to run it. That cost accrues per second, whether or not the machine is doing anything useful. So the economics are entirely about utilization. Cost per token is the cost per second divided by tokens per second. Everything in this act was a scheme to raise the denominator. And now we can say why serving frameworks are as complicated as they are. Because every piece of that complexity is buying utilization in a memory-bound regime. Continuous batching keeps the batch full, so arithmetic intensity stays high. Page detention stops memory waste from limiting batch size. Prefix caching avoids recomputing shared prompts. Quantization halves the bytes. Speculative decoding spends idle arithmetic. Chunked prefill interleaves compute-bound prefill work with memory-bound decode work so that both resources are busy at once. Which is, when you look at it, the neatest trick in the whole stack. 2 workloads that are each bottlenecked on a different resource. Run together, each filling the other's idle capacity. Now, the tension that shapes every product built on this, and it is worth stating because it explains pricing you have probably wondered about. Throughput and latency trade against each other, and they are not two goals. They are two ends of one curve. Batch size is the dial. Turn it up and cost per token falls while time per token rises. Turn it down in the reverse. This is why the same model is sold at different prices for different service levels and why the cheap tier is slower. It is not artificial segmentation. It is a genuinely different point on the roofline, and the vendor is passing on a real difference in utilization. It also explains why long context is expensive out of proportion to its length. Longer context means a larger KV cache per request, which means fewer concurrent requests fit in memory, which means smaller batches, which means lower arithmetic intensity, which means worse utilization, which means higher cost per token. For every user on that machine, not only the one with the long context, and it explains the industry's obsession with the memory capacity of accelerators, which from the outside looks like a strange thing to care so much about. Capacity determines batch size. Batch size determines arithmetic intensity. Arithmetic intensity determines whether the arithmetic units are working or watching. Capacity is throughput. That is the sentence. One honest caveat before Act 5, because I have simplified. Real deployments are not one model on one GPU serving uniform requests. They are heterogeneous fleets, mixed request lengths, bursty arrivals, latency guarantees, multi-tenancy, and failures. The scheduling problem is genuinely hard, and the difference between a good serving system and a mediocre one is often larger than the difference between two generations of hardware. But underneath all of that sits the same physical fact we started with 3 hours ago. The weights have to be read. Reading them takes time. Everything else is an attempt to get more value out of each read. Act 5 is about what happens when the model does not fit on one machine at all. When the memory hierarchy grows a tier made of network cable, and every problem in this film returns larger. Everything in Act 4 was inference. Training is a different problem, bound by a different resource. And the confusion between them is why people draw wrong conclusions about hardware. Inference at batch 1 is bandwidth bound with an arithmetic intensity of 1. Training runs at large batch, so arithmetic intensity is high and you're genuinely compute bound. Those advertised flops are real here. But you trade one constraint for another because training's binding limit is capacity. Consider what must be in memory to train per parameter. The weight itself in half precision, 2 bytes. Its gradient, 2 more. But you cannot update weights in half precision. The updates are tiny relative to the weights and would vanish in rounding. So you keep a full precision master copy, 4 bytes. And the optimizer, if it is, Atom keeps 2 running statistics per parameter in full precision, 8 more, 2 plus 2 plus 4 plus 8, 16 bytes per parameter before a single activation. For a 7 billion parameter model that is 112 gigabytes. The model itself is 14, you're carrying 8 times the model's own size. In machinery for improving it. A 7 billion parameter model, small by current standards, trainable in the sense that people do it routinely, already exceeds a single 80 gigabyte accelerator before any activations. That is why distributed training is not a technique for frontier labs. It is the default at almost any scale worth doing. Then activations. The backward pass needs the forward pass's intermediate values to compute gradients. So every activation must be kept from when it is produced until it is consumed on the way back. Activation memory scales with batch size times sequence length times hidden dimension times depth, and at long context it can exceed everything else combined. The Zero Infinity authors put the historical mismatch starkly. The largest dense models grew over 1,000-fold in 3 years, while GPU memory grew 5-fold. From 16 gigabytes to 80, 1,000 against 5. That gap was closed almost entirely by systems work, by distributing state across many devices, rather than by memory getting bigger. And it produced the fact that best captures the era. It required 800 V100 GPUs just to fit a trillion parameter model for training. Not to train it in reasonable time, to hold it. 800 accelerators as a container. So the shape of the training problem is the opposite of inference. Inference asks, how do I move these weights fast enough? Training asks, where do I put all of this? And how do the pieces talk to each other? Both are memory problems. They are different memory problems, and the rest of this act is about the second one. The 16 bytes per parameter figure has a story inside it that is worth telling because it is the clearest example in this film of numerical precision being a systems decision rather than a mathematical one. Training was originally done entirely in 32-bit floating point. 4 bytes per number everywhere it worked, and it was twice as expensive in memory and bandwidth as it needed to be. The obvious move is 16-bit, half the bytes, half the traffic, and on tensor cores roughly double the arithmetic throughput. The problem is that naive half-precision breaks training, and it breaks it in an instructive way. The original 16-bit float format, FP16, has 5 exponent bits and 10 mantissa bits. 10 mantissa bits is decent precision. 5 exponent bits is a narrow range, and range is what gradients need. Gradients during training are frequently very small and values below the format's smallest representable number flush to 0. Gradients vanish, not for any mathematical reason, purely because the number format could not represent them. 2 fixes and both are in use. The first is loss scaling. Multiply the loss by a large constant before the backward pass. So gradients land in representable range, then divide it out before the update. Pure bookkeeping, and it works. The second is a better format. BF16 keeps 16 bits but reallocates them. 8 exponent bits, 7 mantissa. It has the same range as FP32, and less precision. For training, that is exactly the right trade, because networks tolerate imprecision well and tolerate absent values. Not at all. BF16 needs no loss scaling and has largely become the default. That is a genuinely interesting result about deep learning, and worth stating on its own. These models care far more about dynamic range than about precision. 7 bits of mantissa, about 2 decimal digits, is enough to train state-of-the-art systems. The information is in the aggregate behavior of billions of parameters, not in the low-order bits of any of them, which is also in a different costume, why quantization works at inference time. But you cannot use 16 bits for everything, and this is where the master copy comes from. Weight updates are typically many orders of magnitude smaller than the weights themselves. Add a tiny number to a large one in 16-bit, and the result rounds back to the large one. The update is silently discarded, and training stalls with no error anyway. So, master weights in 32 bits, updates applied there. Forward and backward passes in 16. That is mixed precision training, and it is why the per-parameter budget carries both a 2-byte and a 4-byte copy of every weight. The frontier now is 8-bit training, which is genuinely hard for the reasons above amplified. Less range, less precision, more places where something silently becomes 0. FP8 has hardware support on current parts, and it is used successfully for parts of the computation. Whether full FP8 training becomes standard is open. The pattern, though, is stable, and it is the same one from the quantization beat. The field keeps discovering that it needs fewer bits than it thought, and every reduction pays out twice, in bandwidth and in arithmetic throughput. Activation memory is the most flexible part of the training budget because there is a trade available that exists nowhere else in this film. You can choose not to store something and compute it again instead. The backward pass needs forward activations. The default is to keep them all. Gradient checkpointing keeps only some, say the input to every few layers. And when the backward pass needs an activation that was not kept, it recomputes it by rerunning the forward pass from the nearest checkpoint. You're spending arithmetic to buy memory, and the exchange rate is remarkably good. Chen and colleagues showed you can train an n-layer network in memory proportional to the square root of n at the cost of 1 extra forward pass per mini-batch. Square root memory for roughly 30% more compute. In their measurement, a 1,000-layer residual network went from 48 gigabytes to 7, with 30% additional runtime, 48 to 7. A factor of 7 in memory for a third more time. That trade is worth taking almost always, and the reason is the thesis of this entire film. In a machine where arithmetic is abundant and memory is scarce, any exchange of arithmetic for memory is favorable. You're spending the thing you have too much of, and notice that the same trade appears at every level of the stack, which is how you know it is fundamental rather than a trick. Tiling recomputes indices to avoid storing intermediates. Flash attention recomputes attention weights in the backward pass, rather than storing the quadratic matrix. Checkpointing recomputes activations. Everyone is arithmetic spent to avoid touching memory, and everyone wins. There is a limit, and it is worth naming, so this does not sound like free lunch. Recomputation is not free. It is 30% here, and it is more if you checkpoint more aggressively. Push it far enough and you're recomputing so much that compute becomes the constraint again, at which point you have simply moved the bottleneck back where it started. The optimum is somewhere in the middle, and it depends on your model, your batch size, and your hardware. The general principle is the one to keep. Memory and compute are exchangeable at a rate set by the hardware, and the current rate strongly favors spending compute. That rate is not a law. It is the ratio between flops and bandwidth, and Act 1 told us that ratio has been moving in one direction for 20 years at 3 times versus 1.6. So the trade gets more favorable every hardware generation. Techniques that were marginal 5 years ago are obviously correct now, and techniques that look extravagantly wasteful of arithmetic today may be standard in 5 years. If you want a rule of thumb for predicting where systems research goes next, assume arithmetic keeps getting cheaper relative to memory, and ask what that makes worth doing. The model does not fit, so you use many machines and now you have to decide what to split. And there are several answers, each solving a different problem, and each with a different communication cost. The simplest is data parallelism. Every device holds a complete copy of the model. The batch is divided among them. Each computes gradients on its slice, and then all devices average their gradients, so every copy applies the same update and they stay identical. This is beautiful when it applies. Compute scales nearly linearly. The implementation is simple, and the only communication is the gradient average, once per step on a fixed volume equal to the model size, independent of batch size. That last property is the key to why data parallelism scales. Increase the batch per device, and you do more compute per step with the same communication. The ratio of compute to communication improves, so larger local batches make the parallelism more efficient. And its limitation is exactly the one from beat 38. Every device holds a full copy of weights, gradients, and optimizer states. 16 bytes per parameter on every device. Data parallelism does nothing for capacity. It replicates the problem rather than dividing it. So it works only when the model fits on one device, which, for anything modern, it does not. The fix is elegant, and it is what 0 does. Notice that the replication is waste. Every device is storing an identical copy of the optimizer states, and each one only needs the slice it is updating, so shard them. Each device keeps one shard of the optimizer states, one shard of the gradients, and in the most aggressive form, one shard of the parameters, gathering the others temporarily when needed. This preserves data parallelism's simple programming model while removing its capacity problem, and it converts the saving into extra communication. Parameters must be gathered before use and released after, which is fine because gathering can be overlapped with computation on the previous layer, the same overlap trick from the offloading beat in Act 3. That is what makes zero infinity work. It shards state across devices, spills further to CPU memory and NVMe, and hides the transfers behind compute, sustaining over 25 petaflops on 512 V100s at about 40% of peak. 40% of peak while streaming parameters from NVMe is a genuinely impressive systems result, and it rests entirely on the fact that training has predictable access and enough arithmetic per byte to hide the transfer behind. But data parallelism, sharded or not, has a floor. A single layer's computation happens on one device. If a single layer's weights and activations do not fit, no amount of data parallelism saves you, because data parallelism never splits a layer. For that, you need to cut the model itself, which is the next beat, and where communication stops being an occasional synchronization and becomes part of the forward pass. There are two ways to cut a model, and they are orthogonal across a layer and between layers. Tensor parallelism cuts across. A matrix multiplication can be split by columns. Each device computes some output columns, using the whole input and its slice of the weights. Each device holds a fraction of every layer's weights, and computes a fraction of every layer's output. The catch is that the outputs must be recombined before the next operation, so devices must communicate within every layer, in both the forward and backward pass. That is not a synchronization at the end of a step. It is communication in the innermost loop. Megatron LM showed this can be done efficiently with a small number of communication operations inserted into standard framework code, and reported sustaining 15.1 petaflops across 512 GPUs at 76% scaling efficiency. 76% across 512 devices with communication inside every layer is a very strong result. And it is only possible because those GPUs are connected by NVLink within a node. Tensor parallelism is essentially always confined inside a single server for exactly this reason. Stretch it across a slower network, and the per-layer communication dominates and efficiency collapses. Pipeline parallelism cuts between device 1 holds layers 1 through 8, device 2 holds 9 through 16, and so on. Activations pass from one to the next. Communication is now small, only the activations at the boundaries, once per stage, and it does not scale with model width. That makes pipeline parallelism suitable across slower links, and it is how models are split across nodes. Its problem is different, and it has a name: the bubble with one batch in flight. Device 2 waits for device 1, device 3 waits for device 2. Most devices are idle most of the time. The fix is to split the batch into micro batches and keep several in flight, so that while device 2 works on micro batch 1, Device 1 is already on microbatch 2. The bubble shrinks as the number of microbatches grows, but it never reaches 0, and the memory cost rises because several microbatches activations are live at once. In practice, large training runs use all three at once: data, tensor, and pipeline in a configuration chosen to match the machine. Tensor parallelism inside a node where NVLink is fast. Pipeline parallelism across nodes where the network is slower. Data parallelism across the whole cluster with sharded optimizer state. And the configuration is not a matter of taste. It is determined by the bandwidth hierarchy of the physical machine. What is fast within a package, what is fast within a node, what is slow between nodes. Which is the point I want to leave this beat on. The parallelism strategy of a frontier training run is a map of the interconnect. The software layout is a picture of the cabling. Somebody's model architecture is shaped by which wires happen to be fast. And that is the memory hierarchy again, one tier further out, deciding the structure of the thing being built, which makes the network the last tier of the memory hierarchy. And it behaves exactly like every other tier we have studied. The hierarchy inside a node we have already met: registers, cache, HBM at 3.35 terabytes per second. Then NVLink between GPUs and a server at 900 gigabytes per second, which NVIDIA describes as 7 times PCIe Gen 5 at 128. Then the network between nodes, InfiniBand or Ethernet, at a few hundred gigabits per second, which is tens of gigabytes per second. From HBM to the internode network is a drop of roughly 2 orders of magnitude. And it is the same shape as every other cliff in this film. Another tier, another factor of 100, another set of techniques for hiding it. This is why the physical topology of a training cluster is a first-class design problem. 8 GPUs in a node connected all to all by NVLink through a switch. Nodes connected by multiple high-speed network links. Racks connected by more. It is a hierarchy of bandwidth domains, and the parallelism strategy is chosen to put the chattiest communication in the fastest domain. Now the operations themselves, because distributed training does not do arbitrary message passing, it does a small set of collectives, and their cost structure explains a great deal. The dominant one is all reduce. Every device contributes a value. All values are combined, and every device receives the result. Gradient averaging is an all reduce over the full gradient tensor. The naive implementation is terrible. Send everything to one device, combine, broadcast back. That device's link becomes a bottleneck and the cost grows linearly with the number of devices. The standard implementation is the ring all reduce, and it is genuinely clever. Arrange the devices in a ring. Split the data into as many chunks as there are devices. In the first phase, each device sends one chunk to its neighbor while receiving another, accumulating as it goes. After n WUD steps, each device has one fully reduced chunk. In the second phase, those chunks circulate until everyone has everything. The result is that each device sends and receives an amount of data that is independent of the number of devices. It depends only on the size of the tensor. The all-reduce cost stops growing as the cluster grows. That property is the reason large-scale data parallelism is possible at all. Without it, communication would grow with cluster size, and there would be a hard ceiling on how many devices could usefully cooperate. And then the technique that makes it disappear: overlap. The backward pass computes gradients, layer by layer. From the output backwards, the gradient for the last layer is ready, long before the first layers. So you begin the all-reduce for each layer's gradients as soon as they exist, while the backward pass continues on earlier layers. Done well, essentially all communication hides behind computation, and the step time is pure compute. That is what 76% scaling efficiency across 512 GPUs actually means in practice. Not that communication was cheap, but that it was almost entirely hidden, which is, one final time, the same idea as every other beat in this film. You cannot make the transfer faster. You can make sure nobody is waiting for it. There is a practical dimension to training at this scale that rarely appears in architecture discussions, and that dominates the lived experience of running these systems. At 10,000 devices, something is always broken. The arithmetic is unforgiving. If a single accelerator has a mean time between failures of a few years, which is a good number for a well-run data center part, then a cluster of 10,000 of them has a mean time between failures measured in hours. And a training run is tightly coupled. Every device participates in every step. Every step ends in a collective that requires all of them. One failed GPU does not slow the run down proportionally. It stops the run. So a frontier training job is a computation that must survive the near certainty of hardware failure during its execution. And the system's answer is checkpointing, the other kind. Periodically write the full training state to storage, so that after a failure you restart from the last checkpoint rather than the beginning. Now the costs. and they are memory hierarchy costs, which is why this beat belongs in this film. The state to right is the 16 bytes per parameter budget from beat 38, sharded across the cluster for a large model that is terabytes. Written to storage, which Act 3 established is the slowest tier there is. And the frequency is a genuine optimization problem with a clean shape. Checkpoint too rarely, and a failure costs you a lot of recomputation. Checkpoint too often, and you spend a large fraction of the run writing state instead of training. The optimum depends on failure rate and checkpoint cost, and it is calculable. The techniques for making it cheap are the same ones we have seen all film. Write asynchronously, so training continues while the checkpoint drains. Stage to CPU memory first, fast and dribble to storage in the background. Shard the write so every device writes only its own slice in parallel, turning one enormous serial write into thousands of small concurrent ones. Every one of those is a memory hierarchy technique. Overlap the transfer, use a faster nearer tier as a buffer, and parallelize for concurrency. There is a subtler failure mode worth mentioning because it is the one that runs quietly. Not every failure announces itself. A device can produce wrong results, silent data corruption, from a marginal transistor, a cosmic ray, a link error that slips past its checksum. At sufficient scale, these are not hypothetical, and large operators have reported them. A silent corruption in a gradient propagates into the weights, and now every subsequent checkpoint is poisoned. You may not notice for hours, and the honest remedy is often to roll back to a checkpoint from before you can prove it was clean. I raise this because it puts the rest of the film in perspective. We spent 3 hours on how to move numbers efficiently. At 10,000 devices, you must also consider that some of the numbers are simply wrong, that nothing will tell you, and that your beautifully optimized pipeline is faithfully propagating the error at 3.35 terabytes per second. Efficiency is necessary. It is not, at this scale, sufficient. Let us look forward, using the one thing this film has been careful to establish, the difference between what scales quickly and what does not. The keystone measurement from Golami and colleagues over 20 years. Peak server flops scaled at 3 times every 2 years. DRAM bandwidth at 1.6, and interconnect bandwidth at 1.4. Those 3 numbers are the future, and they are not a forecast. They are 2 decades of observation. Compute is pulling away from memory at roughly twice the rate, and away from the network faster still. And Act 3 gave the physical reason flops are lithography, and lithography still delivers. Bandwidth is wires and packaging and stacked dies, and those improve at the speed of mechanical assembly. So, project it. Every generation, the ratio of arithmetic to bandwidth gets worse. Ridge points move right. More workloads become memory-bound. Techniques that trade compute for memory traffic become more favorable. And the gap between peak specification and achieved performance widens, because the specification tracks the fast-growing number and reality tracks the slow one. The TPU paper made this point in 2017 from the other side, and it is worth quoting the direction of it. The authors note that using faster memory in the TPU would triple achieve throughput. A chip with 65,000 multiply accumulate units and the single highest leverage change available was not more arithmetic. It was better memory that was nearly a decade ago, and the ratio has only moved further in that direction since. So what is the industry actually doing about it? 4 things, and they map exactly onto this film's 5 acts. Move memory closer. HBM was the first step. Stacking memory directly on top of logic is the next, and it is being actively pursued. The limit, as we said, is thermal. The heat from the logic must escape through the memory sitting on it. Move less, quantization, sparsity, mixture of experts, better algorithms. This is where most of the practical progress has come from, and it is the cheapest lever because it is software, reuse more, bigger on-chip memories, better tiling, fused kernels. The TPU's 28 megabytes of software-managed scratchpad was an early bet in this direction, and the bet has been vindicated repeatedly. Specialize. If the operation is fixed, wire it. Tensor cores did this and won 30-fold. Going further means committing harder to a fixed computation, and Act 2 established what that costs permanently at 4 nanometer. And there's one honest caveat I want to leave on the forecast. Because straight-line extrapolation of exponentials is how people embarrass themselves. 3 times per 2 years for flops cannot continue indefinitely. Transistor scaling is slowing, and much of the recent flops growth has come from reducing precision, from FP32 to FP16 to FP8 to FP4, which is a resource that runs out. There is no FP1 worth having. When precision reduction is exhausted and lithography slows, the compute curve bends toward the memory curve, and the imbalance stops worsening. That would be, in a strange way, a relief, but it is not where we are today. And everything in the next several years will be built under an imbalance that is still growing. Before the close and inventory, because a film about committing computation to physical matter should be honest about what has actually been committed, the industry has, over the past decade, permanently etched into silicon. Matrix multiplication at a fixed tile size, several floating point formats, of which at least 2 are already unfashionable, an 8-bit number format designed by committee, video codecs for standards that have since been superseded, ray tracing intersection units, texture filtering hardware present on parts that will never render a texture, and the specific opinion that 32 threads should agree with each other. Each of those was a reasonable decision at tape-out. Several were obsolete before the parts shipped in volume. All of them are still there, drawing power, occupying area, being cooled on every one of the millions of units manufactured, because a wire cannot be patched, and the masks were cut, and the atoms were placed. There's a texture unit somewhere on a data center accelerator in a rack in Virginia that has never filtered a texture and never will. And it will be decommissioned in 8 years, having spent its entire operational life as a very expensive piece of thermally conductive silicon. And as of this film, also permanently committed to silicon somewhere in the world. The proposition established in Act 2, which I will not restate because it is now load-bearing infrastructure and does not need my help, which on the evidence of the preceding list is not obviously the least useful thing we have etched. It is at least still true, which puts it ahead of the video codecs. I raise this seriously as well as flippantly because it is the real cost of specialization, and it is the reason the general-purpose machine keeps winning. Every fixed function unit is a bet that a computation will still matter in 3 years. Tensor cores were a good bet. Matrix multiplication is not going anywhere, and the 30-fold advantage compounded into an entire industry. Many other bets were not, and the market is littered with excellent accelerators for operations the field moved past, while the chip was being fabricated. This is why CUDA's programmability is a more durable asset than any particular arithmetic unit. Software can follow the field, silicon cannot. A chip is a photograph of what its designers believed 36 months before you bought it. And it explains something we noted in Act 2 and left hanging, why several superbly engineered accelerators from well-funded teams with genuinely better silicon for a specific workload have failed to displace the incumbent. They were not beaten on transistor. They were beaten by the fact that the workload moved and the general-purpose machine moved with it, and they could not. The lesson generalizes past hardware. And it is the last thing I will editorialize about before the close. The more precisely you optimize for the present, the more completely you are committed to it. We have gone from a doped silicon crystal to a token. And I want to close by being precise about what this film has shown and what it has not. What it has shown, I think, securely is a single physical fact and its consequences. Arithmetic is cheap, moving numbers is expensive. The gap between them has widened for 20 years and continues to widen. Everything we examined, the design of the GPU, the memory hierarchy, tensor cores, CUDA structure, KV caching, flash attention, quantization, speculative decoding, every form of parallelism is a response to that one fact. That is a claim I am confident in because it was arrived at from several independent directions that agreed, from energy per operation, from the roofline model, from published measurements, and from our own. Now the limitations, in order of how much they should temper what you take away. Our measurements are not of a GPU. Every first-party number in this film came from an Apple M4 Pro, a laptop processor with unified memory and no HBM. The latency staircase, the thread scaling curve, the storage figures, the ridge point, all measured, all real. None of them from the hardware this film is about. What transfers is the shape of the hierarchy and the relationships between tiers. The absolute numbers do not transfer, and we have said so every time they appeared. Vendor specifications are not achieved performance. We used NVIDIA's published figures for the H100 throughout, because for architectural facts, they are the primary source. But the gap between peak and achieved is large and well documented. Megatron LM sustained 30% of peak on a single GPU, and flash attention reaches 25 to 40% on attention. Every calculation in this film that used a peak figure is a bound, not a prediction. The specifications will date. The H100 numbers will be superseded probably before this film is a year old. The ratios will move. The 400 cycle latency, the 80 gigabytes, the 3.35 terabytes per second, treat these as a snapshot of one generation, not as constants. We simplified. Real serving is heterogeneous and bursty. Real training runs use combinations of techniques we describe separately. The arithmetic intensity of 1 for decode assumes dense attention and ignores the KV cache traffic, which at long context is not negligible. Every clean number in this film is cleaner than reality. And we did not cover power delivery, cooling, chip fabrication, and yield, the economics of foundry capacity, networking hardware in any depth, compilers, or the enormous body of kernel-level optimization that makes any of this run. Each is a film. What I hope you take from this is not the numbers. The numbers will change. It is the habit of asking about any performance claim, how many operations, how many bytes, and which side of the ridge point does that put you on? That question is durable. It works on hardware that does not exist yet. It is the question the roofline model was built to make askable, and it survives every change in the specifications, because it is about the relationship between a computation and a machine, rather than about either one alone. And there's one more thing, which is the reason this film exists in the shape it does. The systems we are all currently arguing about, what they can do, what they mean, whether they understand anything, run on doped silicon in a hierarchy of memories, bound not by the elegance of the mathematics, but by how far a number has to travel to reach an adder, and by how much heat that costs. That is not a diminishment. It is where the constraint actually lives. Every argument about capability is downstream of the question of what can be computed at what cost. And the answer to that question is decided by wires. We started with a single token and 140 gigabytes that had to move to produce it. That is still the whole story. Thank you for watching.